校这边的音效那个声音，音效那个声音，那首声音。嘿，我1、2、3，这样都有吧？有的吧？1、2、3。你这样子，你听看1、2，有吗？
那我觉得应该是我这台的问题，应该是我这台的问题，我测打关，我这台耳机也收不到。
没有，它播出来了。它播出来了，刚刚你按的时候它播出来了。 没事，你那边继续吧。
Welcome everyone to the third day of the session, third day of the conference. The first session is on anonymity, surveillance, and tampering. And the first talk will be on anonymous permutation routing by Paul Bunn, Eyal Kushlewitz, Rafael Ostrowski, and Paul will give the talk.
Good morning. Thanks, Manoj. I'm presenting work with Eyal Kushlewitz and Rafael Ostrowski on anonymous permutation routing. So just a brief outline of the talk. I'll introduce the problem and the model, give existing solutions, what was known before our work, a little bit of background, and then dive into an overview of the main ideas of our result. So anonymous permutation routing is our result in a model that was introduced by Shi and Wu in 21. It's called the non-interactive anonymous router model. And in this setting, you have n senders and n receivers. They are connected, so one receiver per sender via some permutation. And the senders have a stream of messages that they wish to relay to the receivers. Rather than peer-to-peer links between senders and receivers, we assume the existence of a central router that will be responsible for all the routing. So the senders send their messages to the router, and the router delivers them to the receivers. In terms of privacy, there are two main things that we want to protect. One is the contents of the message. Only the intended receiver should receive its message. And the second is the permutation, who's talking to who. And that will be the main challenge of the NIR model, protecting the identities of the links. Oops. And in terms of formalizing the model of an adversary, we assume honest but curious adversary, static. And in terms of who's corruptible, so the interesting work happens if the central router is corruptible, so the adversary will always be assumed to corrupt the central router. In addition to that, some subset of the senders and receivers. And the specific subsets that are of most interest in the basic collusion model, the adversary can corrupt up to n-2 sender-receiver pairs. So in particular, this means if the adversary corrupts the sender-receiver pair plus the central router, it's assumed that he can determine the linkage between that sender and receiver, so in particular, what the permutation does between those two. So if he can corrupt up to n-2 pairs, this means there's two senders and two receivers that the adversary does not corrupt, and the permutation, what the permutation does on those two sets of senders and receivers should remain unknown. In the sender collusion model, in addition to the central router, all the senders are corruptible, and in this model, the adversary still should not be able to learn the permutation between the senders and the receivers for the non-corrupt receivers. And the receiver collusion model is just the inverse of that for the receivers. Let me talk about applications and applications that are particularly well suited to each one of these collusion models. So I'm going to put up again a diagram. Arbitrary collusion, which we don't investigate, is if the adversary can corrupt the central router plus everyone except for two parties. And I'll just notice that in the diagram, I've arranged it this way because as you move down the layers of the diagram, the collusion becomes more difficult. So if you have a solution that is secure in one model, then you're automatically secure for the models above it. So in the most basic collusion model, an application would be peer-to-peer messaging, where you want to keep private who is talking to who. For sender collusion model, some interesting applications would be subscription, privacy subscription. So you want the receivers to privately subscribe to some channel. And you assume that the senders perhaps can all collude with the central router, and you should maintain the privacy of which channel each receiver is subscribed to. You can also think of multi-client peer, or like mailboxes as another application where sender collusion would be interesting. So in this case, you have many receivers who are all subscribed to some mailbox, some index, and the stream of messages is the mailboxes as they get updated with new messages. For the receiver collusion model, this was actually the focus of the original NIAR work by Shi and Wu in 21. And one of the interesting applications of that, which we won't go into here, is a non-interactive anonymous shuffle, as well as the flip side of multi-client peer and multi-client writing. And although we don't explicitly talk about it in our paper, you could also consider interesting applications where, unlike the other models, the central router is always assumed to be corruptible by the adversary. There may be some settings, for example, if this is used as a sub-protocol, where each party takes turns acting as the central router. There may be interesting applications where you assume the central router is honest, and then talk about what happens if some set of the other parties are corrupt. An oblivious shuffle is something that you could get out of such a device. So in our paper, we focus on the top and the left collusion models. Okay, so let me go into some background of what was known before our work. So one thing I'll emphasize is that the messages are message streams. So it's not just a single message that each sender wants to communicate to the receiver. So as such, we allow at the beginning a setup phase. And in the setup phase, the messages, it's like an offline phase, so we don't have the messages yet, but we do have access to the permutation. So in the setup phase, for example, you can exchange keys. So each receiver could get a decryption key that corresponds to some public key that is delivered to the corresponding sender with respect to the permutation. So one naive solution to the NIAR problem is just to use flooding. So the senders all send their encrypted message to the central router, and the central router bundles them all up and delivers all N messages to every single receiver. But then the receiver has one decryption key and decrypt exactly one of those messages, the one that's intended for it. So this solution works. The encryption gives you the message privacy part of the security. Then the fact that it's just flooding gives you the privacy of the permutation. The problem with the solution is that it's not very efficient. It requires n squared total communication. Here n is the number of senders and receivers. And it also requires n squared work at the central router. In order to reduce the communication, you could pose this as a peer problem. So still the senders all send their encrypted messages to the central router. The central router acts as a peer server. So each receiver now sends a peer query that fetches the appropriate index that they're looking for, and the central router responds with a peer response. So this solution benefits. You have reduced communication from n squared to quasi-linear, but it's still, because peer is linear in the size of the database, you still have n squared work of the central router. We saw some talks earlier talking about how you here can enjoy offline mode to reduce the server computation time. In this setting, that doesn't work because the messages are not fixed. It's a stream of messages. Every round there's a new message. So it would require doing the setup over and over again, and you wouldn't end up seeing the enjoyment of the reduction of n squared computation at the central router. And finally, in the original work that introduced this model by Shi and Wu in 21, they had similar metrics as just using peer with quasi-linear communication, n squared computation. One benefit over the peer model is that their solution gives you protection against receiver collusion, which is one of the adversary collusion models that we don't go into. And actually, as concurrent work, there's a follow-up to Shi and Wu's original paper that will be presented immediately after me by Nikhil. Just a quick comparison. I won't go into the details of their work because I don't know them exactly and because he'll be presenting it. But just a quick comparison of what they attempt to do and what we attempt to do. So first, we consider different collusion models. While we focus on the top and the left, they focus on the right, and namely the receiver collusion. They have similar performance results in that things are quasi-linear, which is as well as could be expected. But in order to get protection against receiver collusion, which appears to be the more challenging protection to provide, they need to use results from obfuscation. Okay, so the motivating question that we had when we when we started investigating this problem was there a solution in the NIR model that reduced the naive solutions from n squared computation at the central router down to quasi-linear, which is as best as can be expected. And furthermore, does a solution exist under standard cryptographic assumptions? So obviously, if I put these questions up, the answer to these questions is yes. Before I state the theorem statement, just some quick background. So rate 1 OT was introduced by Dutlin et al. In 2019, and it's rate 1 OT and rate 1 peer are just like standard OT and peer variants, except the server response is basically the same size as the messages or the peer database, some constant stretch, and this will be important for our results. So our theorem, assuming rate 1 OT, which is, I forgot to mention, it's you can get, based on these results from Dutlin et al. And others, there are known instantiations of rate 1 OT and rate 1 peer based on DDH, QR, and LWE, so very standard assumptions. So our theorem, assuming rate 1 OT, there is a solution to anonymous permutation routing against the honest but curious static adversary who is allowed to corrupt the central router and under the sender collusion model and basic collusion models that achieves our quasi-linear results. I just have a couple minutes, so I just want to give some high-level ideas to our solution. So as our title, anonymous permutation routing suggests, our result is based on some ideas from permutation routing. So what is permutation routing? Permutation routing without anonymity is you still have n senders and receivers. Again, they're not connected by peer-to-peer links, but rather they're connected via some routing network, which you can think of as like a sorting network. And just like in the expander graphs talk we saw yesterday, these permutation networks have some special properties that apply nicely to our setting. And in fact, we think that perhaps these permutation networks might be useful in other cryptographic results as a building block, just as expander graphs were yesterday. So the idea is the network is fixed ahead of time, and you don't know what the permutation is. And then once the permutation comes in, you choose random paths that respect that permutation. So you go through the various sender-receiver pairs and pick paths. And the idea behind permutation routing networks, good ones, they're small, which means overall quasi-linear or polylog depth. And also with high probability, you want the paths that you select to not collide so that you can successfully route messages without collisions. And so that's called an edge disjoint property. And our observation is that because these networks are small, even though we don't have actual networks, we can have the central router emulate the routing network. And the key problem here is because the permutation needs to remain hidden, if we're going to have a single party, the central router, which is corruptible, emulate it, then he needs to make his routing decision without knowing what he's doing. And so we create the notion of an obfuscated gate, which allows the central router, you can think of it as acting as a little mini peer server for every node in the routing network, where he obliviously takes messages on the incoming wires, flips them around, permutes them, and outputs them. And so the actual values that get written are the peer queries. So this slide just overviews how these results, or how these ideas are put together. One final comment I'll make is that the edge disjoint property of permutation networks is not quite enough. We had to prove a little stronger result to actually guarantee security in our anonymity proof. Okay, thank you.
Thank you. Any quick questions? So I had a quick question. So is there any restriction that you're restricting to permutations? Is that a real restriction, or could you handle routing which is not permutation?
Yeah, so in terms of the metrics, you'd have to you have end senders and end receivers. We do use permutation routing networks, which have nice properties for permutation. So depending on what you're trying to do, you could certainly do other things. One thing we've thought about is, you can view the end party thing as actually two parties, and each party is representing as n bits of information or a database of size n. So there are different things you can play around with. You can also generalize the model a little bit. Instead of each receiver exactly subscribing, say, to one receiver or one sender, it subscribes to some group of them, and you can play around with different constants and
Thanks.
things like that.
Let's thank the speaker again. Okay, the next talk is on non-interactive anonymous router with quasi-linear router computation by Rex Fernando, Elaine Shi, Pratik Soni, Nikhil Vanjani, and Brent Waters, and Nikhil will give the talk.
Hello, thanks for the introduction. I'm Nikhil, and I'll be presenting our work on non-interactive anonymous router with quasi-linear router computation. This is joint work with Rex, Elaine, Pratik, and Brent. So let me start with introducing the non-interactive anonymous router model. As you just heard about it, there are n senders in this setting, S1 through Sn, n receivers, R1 through Rn, which are, there's a one-to-one mapping between all of them, which can be represented as a permutation pi. And the goal is that we want to route messages from the senders to the receivers via a single untrusted router. And it needs to be done in a non-interactive way while preserving some kind of anonymity. There are 4 algorithms in this scheme. The setup is done by a trusted third party, which gives some sender keys to each sender. Each receiver gets a receiver key, and the router gets a routing program. Then what the senders can do is they can use their sender keys to encrypt messages and send to the router. The router can run the routing program on the sender ciphertexts and obtain some receiver ciphertexts and forward them to the appropriate receivers. Lastly, they can decrypt the messages using the receiver keys. So in this model, let's look at what anonymity means. We study receiver insider protection. Over here, what we want is that the adversary should not be able to learn the honest senders of corrupted receivers. Let's understand this by a simple example where the adversary corrupts the router, all the receivers, and all but 2 senders. So when you corrupt a sender, adversary is allowed to learn the receivers as part of inherent leakage. And consider for a simple case that the permutation is just an identical mapping, I to I. So if you corrupt S3, you learn it's communicating to R3, and so on. S4 is communicating to R4, and Sn is communicating with Rn. Now, the challenge is if you now corrupt R1 and R2, we want to somehow ensure that you still can't learn that who S1 and S2 are talking to among these 2 receivers, and we want to protect this anonymity. So a quick comparison with what was just presented. The sender insider protection is the dual of receiver insider protection. Over there, you want to protect anonymity of receivers if you start corrupting some senders. And what we know is near with RIP is comparable to multi-client functional encryption with function hiding security, which is known from standard assumptions on pairings. Further, near with SIP is comparable to private information retrieval, as you just heard, and which is known from standard assumptions without pairings, such as DDH, QR, LWE. So from a technical viewpoint, it seems that achieving receiver insider protection is a bit more challenging than sender insider protection. Okay, so it's challenging, but why do we care about studying receiver insider protection? The idea is that it is very suitable to study non-interactive anonymous shuffler. In this setting, we have a single untrusted shuffler who receives messages from n senders, and it wants to shuffle the messages and just learn what the output is. And we want to, for anonymity, what we want is the shuffler should not learn which message comes from which sender. And this shuffler setting can be instantiated using near as follows. The shuffler can run the tasks of the router as well as all the N receivers, R1 through Rn. So this enables doing shuffling. But the key observation over here is this requires receiver insider protection because the shuffler has all the receiver keys and we are trying to protect anonymity of the senders. And sender insider protection is insufficient for this scenario. Now, having motivated why do we care about receiver insider protection, what do we know about it? So the work of Shi and Wu showed how to build such a near scheme with O of n communication and O of n square router computation. And they built it from decisional linear assumption on bilinear maps. So a key observation over here is if we did not care about anonymity, then there's a straightforward solution. The senders can just send the messages to the router, which can apply the permutation and forward the messages to receiver. So you can do it in order n router computation if we did not care about anonymity. So there's this gap, and the question then is, can we build near schemes with subquadratic router computation? So we try to answer this question and we achieve some results as follows. We obtain order n log n communication and n polylog n router computation. So essentially, just paying a little in communication, we can drastically bring down the router computation from n squared to quasi-linear. And we note that this is near optimal. We built it from one-way functions and indistinguishability obfuscation. And just to note, in the previous talk you heard about near with sender insider protection. They achieve similar results. They obtain n polylog n router computation, but that's in the sender insider setting, which is incomparable to receiver insider, and the applications, as you heard, are also different. So the roadmap for rest of the talk is going to be as follows. I will first present a strawman construction based on a single IO program. This strawman will have poor router computation because it will obfuscate a very large program, but it will give us some insight of how a main construction works. And then I will present the main construction, what ideas do we need for that, and intuition of what challenges we face while proving security. So let's start with obfuscation. Indistinguishability obfuscation provides a way to obfuscate a program P into an obfuscated version I of P. For functionality, we want that on any input, the two programs should output the same value. And for security, we want if two programs P and Q are functionally equivalent, then their obfuscations should be computationally indistinguishable. And there has been a lot of work studying indistinguishability obfuscation, and recently Jain et al. Showed how to build it from well-studied assumptions. So how can we use a single IO program to do the near task? Suppose that the senders and receivers have some encryption-decryption keys. Then to the router, we can provide the obfuscation of the following program. This program hardwires as secrets the permutation pi and all the sender and receiver keys. And the program is very simple. You just decrypt all the ciphertext using sender keys, apply the permutation on these messages, and encrypt using the receiver keys, and just output these ciphertexts. So what can we say about this? While we don't know if this would be secure or not, the main problem that we come across is it has poor router computation because the known IO constructions incur poly blow up in evaluation time. And over here, the original program takes O of n time because there are n ciphertexts you are executing on. So clearly this IO program will run in poly n time, which the router needs to execute, and this is bad. So how can we go about solving it? The idea is, instead of obfuscating a single large program, we will obfuscate a lot of small programs, and these programs will be gates in a routing network. So let me tell you about construction next. Let's start with what's a routing network. Over here, I will just consider 4 senders and receivers, and the idea is generalized to any n. Apart from senders and receivers, there are some intermediate nodes in this routing network denoted by I, and messages are routed from senders to receiver via these multiple layers, and the gates perform the routing. The nice properties of routing network are that all receivers are reachable from every sender, as can be seen by these paths. And what this helps with is we can in fact simulate the permutation pi using this routing network. So over here, the 4 senders are mapped to different receivers via these 4 disjoint paths. And we can observe that simple routing networks are not anonymous. Consider that we just corrupt 2 senders, S1 and S4. Because the adversary is allowed to learn their receivers, it learns the 2 red paths taken by them. Then it can infer that the honest sender S2 is communicating with R3 because there's a unique path. So this is clearly not anonymous. So how can we solve it? The idea is if we introduce some filler wires in this routing network, then we can hope for some kind of anonymity. The filler wires don't contain any messages, they just have some dummy messages that they are routing. So what happens now? As before, you learn the messages for the paths for the corrupt senders. But now for the honest sender S2, you learn that it can be taking one of the 3 possible intermediate nodes in the first layer. And crucially, all these wires feed into both the gates, gate 2.1 and gate 2.2. And as a consequence, in the last layer, all possible wires apart from the corrupt wires could be where S2 is routing. And thus, adversary can't infer if S2 is sending to R2 or R3. So using these filler wires, we can hope for some kind of anonymity. And the construction then is as follows. What we do is obfuscate each of these gates in the routing network and provide all the gates to the router. And what the router does is, for routing, it emulates this whole network on its own, meaning it obtains these 4 ciphertexts, 2 from senders, 2 filler ciphertexts, applies the obfuscated gate 1.1 on them to get 4 intermediate ciphertexts and so on for each of the gates in a layer by layer way. And okay, we can hope for the router to emulate this task, but there's a problem. If the router does not emulate it correctly, it can do some mix and match in between and maybe it breaks some anonymity. So how do we go about fixing this? We need to do some kind of authentication checks in this. And our gates then are as follows. We first decrypt to obtain some signed messages, verify some signatures, permute the messages, sign the messages, and re-encrypt the signed messages. So now we want to do some authentication of this kind inside all these gates. Let's look at the efficiency of this construction then. In this routing network, there are n log n gates, where each gate is now polylog n size. As a consequence, even after obfuscation, it's some other polynomial, but still a polylog n. And the router computation then is n polylog n. So this meets our efficiency requirements. And let me quickly give you an idea of what are the challenges. We know that obfuscation is difficult to work with for the building blocks that we are using, and we need some kind of puncturing-based techniques. And over here, what we need is somewhere statistically unforgeable signature scheme, which has a normal and a binding mode. In the binding mode, the signing key should be such that no messages in some set X can be signed, and no valid signatures exist for messages in a set X for verification key. This means that there is some statistical unforgeability on some points, specifically this set X. And further, we require a strong property for security. We want that binding signing key and normal verification key are computationally indistinguishable from binding signing and binding verification keys, which is not satisfied by any of the previous puncturable signature schemes. And our key contribution is showing how to build this SSU signatures from one-way functions and I/O. So just a quick note on additional results. We also initiate the study of adaptive corruptions, and we show that we can perform near with adaptive corruptions for senders and receivers for indistinguishability style security. Particularly, we show a compiler which upgrades any near scheme secure against static to near secure against adaptive corruptions. And this is a generic compiler. It works for receiver insider protection, sender insider protection, and differential anonymity as well. Further, we show that simulation security is impossible to achieve, and we show this via a compressing argument. Lastly, if there's one thing that you want to take away from this talk, it should be the following, that I/O is not only a tool to build complex cryptographic primitives, but it can also be used as a way to boost efficiency of systems, as I just demonstrated. And then there are some natural open questions after this. One is, can you build efficient near from standard assumptions without using I/O? And more interestingly, can the network of IO approach be used elsewhere? Like, can you build more applications beyond this routing task? And even more challenging is, can you boost efficiency of IO itself with such an approach? And with that, I will leave you. Thank you so much.
Okay, thank you. Let's thank the speaker. Since we're out of time, maybe the next speaker can set up. There's a question while the next speaker sets up. Okay, let's thank Nikhil again. The next talk is on lower bounds on anonymous whistleblowing by Willie Quach, Lakia Tyner, and Daniel Wicks. And Lakia will give the talk.
Hello, everyone. My name is Lakia Tyner, and today I'm presenting lower bounds for anonymous whistleblowing. This is joint work with Willie Quach and Daniel Wicks. So let's start by introducing the setting for an anonymous transfer. Here we have a group of friends who are participating in some public conversation over Twitter or Facebook. Here they're having a conversation about bunnies. Here each friend is sending a message through their public account, and so Alice can see all the messages that were sent by Bob, Freddie can see all the messages that were sent by Cecilia, and so on and so forth. In this case, we have one friend who wants to transmit some secret message, possibly completely unrelated to bunnies. Let's say, for example, the secret Krabby Patty formula. And they want to do this possibly without the knowledge of their friends, and also especially without revealing their identity. And so in order to do this, they send particularly crafted bunny messages such that later on, when the conversation has ended, anyone who has access to this public transcript of the conversation can then go back and recover the secret message and do so without realizing that Alice was the one who sent the secret message. A protocol in this particular model is ideal for facilitating whistleblowing. This is because it's likely that the whistleblowers are acting in an untrusted environment. And so if they're identified, they run the risk of facing harsh punishments. And so a natural question that we can ask, and one that is studied in prior works, is can we mitigate this risk using some cryptographic techniques? Anonymous transfer was initially introduced last year by Agricola, Couteau, and Meyer. And this particular model is novel in this situation because it doesn't rely on any trusted parties beyond the non-centers generating some dummy traffic. On the other hand, all other works on anonymous communications require that the trusted parties actively participate in the protocol. And so a technical detail about this anonymous transfer model is that we can model the dummy messages as uniformly random messages. And this is without loss of generality, since we know how to embed uniform randomness in other distributions. The ACM 22 paper has two particular results. The first is a positive result, which states that on one end of the spectrum, we have a very weak form of AT that is possible. And on the other hand of the spectrum, on the other side of the spectrum, we have a very strong form of anonymous transfer that is impossible. And so this leaves a big unknown gap in between these two results. And in this work, we show that we can close this gap by extending the negative results. And this will in turn show that their very weak form of anonymous transfer is the best that we can hope for. Before we more closely describe our results, let's look at anonymous transfer. It is a protocol with C rounds involving two parties, a sender and a non-sender. And as an aside, the lower bounds in a two-party setting imply lower bounds in the n-party setting as well. The AT algorithm include a trusted setup algorithm, which outputs a CRS, a transfer protocol, which takes as input a secret message, which we hope to transmit, which call this mu, and then outputs some transcript of the conversation. And then we have a reconstruct algorithm, which takes as input that transcript and then reconstructs some message mu prime. We also have the correctness property, which states that for all messages mu, the probability that mu prime is not equal to mu is negligible. Additionally, we have this delta anonymity, which describes some distinguishing advantage, and basically says that for all PPT distinguishers and all messages mu, the probability that the distinguisher outputs 1, and we're looking at a transcript pi A, where A is the sender, and another transcript pi B, where B is the sender, is less than or equal to delta. So let's compare our results. The negative result of the ACM 22 paper states that we cannot get a negligible anonymity delta against all polytime adversaries. And then their positive result states that it is possible to build an AT with anonymity delta equals 1 over the number of rounds, but only against fine-grained adversaries whose runtime is a factor of OFC larger than the runtime of the honest parties. This unfortunately relies on some strong assumptions such as ideal obfuscation. And so the gap between these two results leaves open these questions. Can we get a decent anonymity against all polytime adversaries, even though we can't get negligible anonymity? And can we get a negligible anonymity against fine-grained adversaries, even if we can't get it against all polytime adversaries? In this result, in this paper, we show that no, we can't get either of these things. More particularly, our first negative result says that we cannot get security against all polytime adversaries with any non-trivial anonymity that's less than 1. And then our second negative result shows that we cannot get negligible anonymity even in the case where we're considering fine-grained adversaries. Okay, and so we present our results in the form of designing attacks against the anonymity of an anonymous transfer protocol. The goal of these attacks is, of course, to, given the transcript of a protocol, identify who the sender is. And so in order to do this, we consider some notion of progress towards correctly recovering the message, particularly progress associated with a partial transcript pi I, where the first I messages of pi I are equal to the first I messages of pi, and the remaining messages are uniformly randomly sampled. We then conjecture that the party who has made the most progress towards ensuring that the message is correctly recovered is the actual party who sent the message. Okay, and so we have pi I to be defined as the probability of correctly returning the message or recovering the message after the ith message has been sent, and we associate this with pi I. Let's take, for instance, the case when party I has sent the ith message, party A has sent the ith message. We want to assign the progress made between pi minus 1 and pi to that party. And then the main insight that we will use in our attack is that the non-sender messages do not on expectation change the value of pi. This is because the probability that a random message increases correctness is low. And so the blueprint of our attack is as follows. First, we will estimate each party's contribution, and then we're going to argue two things. The first thing is that the contribution of the non-sender is small. And secondly, the total contribution is large, and so that means that the party who contributed the most must be the sender. And then we abstract our blueprint into what we call a covert cheating game, which is a game between two players who alternate updating the state of this game. In this case, we have the position of the dot along the line as the state of the game. We have one player, which we call the bias player, whose purpose is to push the state of the game closer to 1. And then we have a non-biased player who's restricted to making only moves that cannot on expectation change the state of the game or change the position of the dot along the line. We have this third player, who we call an observer, who is given the state of the game at each point from P0 to Pf. And using these points, they're trying to determine which player is the biased player and which player is the non-biased player. And so the main fact that we will use in our attack or in our insight is that the non-player, again, cannot change the state on expectation. And so this means that if PI minus 1 is close to 0 and PI, that means that PI cannot very well be far from 0 in this case. And we show that this follows by Markov. Considering this, this means that we want to weigh the progress made closer to 0 higher. And this will signal to us that that if a player made larger progress close to 0, then that player is likely to be the sender. And so for this, we consider a multiplicative form of progress. So from PI to PI minus 1 to PI, we have this ratio, which is equal to PI over PI minus 1. And so this means that the total progress is the product of all these ratios, which is equal to the final state divided by the initial state. Again, since the total progress made is equal to the final state over the initial state, it must be the case that one player has a total progress greater than or equal to the square root of PF over P naught. And so let's consider N to be the set of indices for the non-biased player. Then, since the total contribution for the non-biased player on expectation will be equal to 1, by Markov, this means that the probability that the total expected contribution or the total contribution made by the non-biased player is greater than or equal to the square root that we saw earlier is going to be less than or equal to the square root of P naught over PF. And then we're going to use this intuition in order to generate or in order to design our attack. So the high-level insight is, first, we're going to estimate each PI. Then we're going to compute the contribution of each player. And then we're going to declare the biased player to be the one who has a contribution greater than or equal to P final, the square root of P final over P naught. So in summary, the ACM 22 paper has a positive and negative result, which has a large gap between the two results. This work closes that gap by extending the negative results. And in particular, we show that we cannot get security against all polytime adversaries for any non-trivial anonymity. And we also cannot get negligible anonymity, even in the case where we're considering fine-grained adversaries. And this will again imply that their positive result is the best that we can hope to get. So I'm going to end with 2 open questions. The ACM 2022 feasibility result relies on ideal obfuscation. And so the question here is, can we construct this under more standard assumptions? And then finally, our covert cheating attack unfortunately runs in a fairly large polynomial. And so the question here is, what can we do to improve the runtime of this attack? Thank you.
Any questions? Okay, if there are no questions, let's thank Lakay again. So the next talk is on multi-instance randomness extraction and security against bounded storage mass surveillance by Jiaxin Guan, Daniel Wicks, and Mark Chandry, and Jiaxin will do.
Thank you, Chair, for the introduction. Hi, my name is Jiaxin Guan, and today I'll be talking about our work, multi-instance randomness extraction and security against bounded storage mass surveillance. It's a really long title, but don't be scared. I'll begin with a very simple example. So over this talk, I will not be touching the technical details, but we'll briefly talk about like what we actually did in the paper. So in cryptography, we are our favorite friends, Alice and Bob, and let's say here they're not doing something super crazy. They're doing a very simple thing. So Alice sends over an encrypted document over to Bob, okay? And you know we can never have an interesting security game with our other friend, Eve. And Eve comes along and doesn't do anything super malicious yet. But what Eve will do is it will eavesdrop on the channel, and while the encrypted message is being transmitted, make a copy of the ciphertext. Okay, that's all Eve will do for now. Doesn't do anything malicious yet, anything super malicious yet. And then Eve will just wait and wait and wait until at a later time, when Eve was somehow able to get the decryption key used by Bob. You can think about Eve get this through a security breach, or maybe through physically interrogating Bob, or by maybe hacking Bob's computer. But anyhow, the adversary gets hold of the decryption key, and now what the adversary can do is can simply use the decryption key to decrypt the ciphertext that it has written down, and therefore retrieve the original secret message that Alice sent to Bob. Okay? So to prevent against this, what we need is what we call forward secrecy. And essentially saying that a secret key compromised in the future should not compromise the security of the messages sent before. But in the standard model, achieving forward secrecy is actually very tricky. We will either require the honest parties to run a multi-round protocol, meaning that they will need to interact in order to send a message, or we will require the receiver, Bob in this case, to constantly update their decryption keys. And both of these could be undesirable under many settings. So what can we do? So one important observation here is that this attack pretty much relies on Eve storing the ciphertext. So the question is, what if the adversary cannot store the ciphertext at all? And how do we actually make that happen? Now imagine in this setting, again, we have our friends Alice and Bob, but in this case, Alice sends over a huge ciphertext to Bob. So it's a very large ciphertext that exceeds Eve's storage. Okay? So when Eve comes along and sees the ciphertext, what Eve can do is can only write down only a portion of the ciphertext, but not the ciphertext in its entirety. And then the transmission is gone, and at a later time, when Eve gets back the private key, but because Eve not only has a small portion of the ciphertext, maybe if we design the encryption scheme in a clever way, we can have that Eve actually gets no information about the message at all. This is exactly what's studied under incompressible encryption. Notice that so incompressible, you can imagine there are two flavors. Well, you can imagine incompressible symmetric encryption. That was studied by Zembowski back in 2006 under the name forward secure storage. And later on, in our prior work, we formalize these ideas and we present incompressible PKE. And we say, okay, Zembowski's constructions actually can be categorized as an incompressible SKE. So the idea about incompressible encryption is that the ciphertext, we make them intentionally huge so that it exceeds the adversary's memory, so that adversary cannot possibly write it down. So in that sense, even if later on we give the adversary the decryption key, the scheme is still secure. Notice that this is impossible in the standard model, because if the adversary has a decryption key, the adversary can do whatever it wants and decrypt the original messages. But here there's one caveat about incompressible encryption, is that necessarily it will require the ciphertext to be much larger than the adversary storage. Okay, so imagine the following scenario: Alice is just sending over a single message, just saying hi to Bob. It's just 3 characters, but in order for it to be encrypted under the incompressible encryption scheme, it will need to be blown up to a huge ciphertext, at least gigabytes or terabytes of data. So this is hugely undesirable in a real-world application. So our question is there any scenario or any security definition that actually makes sense or like would make this incompressible encryption more usable? So now imagine this case. Imagine now Alice sends over the ciphertext is much, much smaller. It's actually smaller than what an adversary can store. But imagine that in the entire system, there are many, many users sending over a huge collection of these ciphertexts. So each individual ciphertext can be small, and the adversary can possibly write it down. But if we consider the entire aggregation of the ciphertext, it exceeds the adversary storage, and the adversary can only store a very small portion of it. Okay, so in this case, we imagine we have some adversary that is trying to do mass surveillance on the entire population. And in here, we assume that, okay, so the adversary has a storage when compared to the total number of aggregation of the ciphertext, it's only a very small percentage, let's say 1%. Okay, so at the end, when the adversary later on is able to get all of the private keys, all of the decryption keys, we want to say that, okay, if you only have around 1% of the memory storage for the ciphertext, then you can only break approximately 1% of the ciphertexts. Okay, and in other words, the other 99% should remain secure. So in other words, if we think about it the other way, if at a later time an adversary decides, hey, I want to attack Bob's ciphertext, well, all it can do is to hope for that when the transmission happened way back, it has actually written down Bob's ciphertext, and that only happens with probability of 1%, assuming that all of the parties is indistinguishable to the like all of the because the adversary don't know who will be the person of interest in the future. So how do we actually construct this? To construct that, one very intuitive way is to, hey, maybe we modify one of the prior constructions of incompressible encryption. So what are the previous constructions? There's the construction of SKE, incompressible SKE by Cymbalski in 2006, and we constructed incompressible PKE back in 2022. And Branko, Dutling, and Dujmovic, they show that you can actually get an incompressible SKE with a rate of 1. Here the rate meaning the size of the size of the message compared to the size of the ciphertext. So that by a rate 1, it's really efficient that your message can be almost as long as the ciphertext. And we also show a rate 1 incompressible PKE where we have a smaller public key. And Branko et al., they also show a incompressible PKE with a rate of 1, but with longer public keys. But in there, their assumptions are much weaker. We notice that among the center of all of these constructions, there's one central piece that's needed. They all use a seeded extractor. A seeded randomness extractor is used in all of these constructions. So now imagine if we want one of the incompressible PKE or incompressible SKEs to be secure across multiple instances, then necessarily what we want is a randomness extractor that is secure across multiple instances. So how do we actually capture this definition, and how do we actually construct such a multi-instance randomness extractor? That's one of the core technical tools that we explored in this paper. So our core technical result is what we call a multi-instance randomness extraction. So the scenario we imagine is as follows. So we have an extractor that is run multiple times, in this case t times, on different sources and different seeds. Notice that the sources here, they can be arbitrarily correlated, okay? And the extractor outputs, let's say here we call them y's. So the sources can be correlated, but what we require is that if we look at the joint distribution of these sources, we say that, okay, we don't assume anything about any specific source. But let's say if we look at the joint distribution, they have a joint mean entropy rate of alpha. And then what we were trying to say is then, okay, if that is the case, then if we look at all of the extractor outputs, we want to say that approximately an alpha t portion of these outputs are statistically close to uniform. Actually, formalizing this intuition isn't very straight, isn't easy. So the core issue here is that notice that any one of these extractor outputs can actually you cannot say such a thing about any specific extractor output. For example, we can imagine where the x they're correlated. For example, we can think about we pick the sources in such a way that we just pick xi to be 0, and all of the other ones we sample uniformly random. Then if for xi, it is not possible for you to extract any useful randomness from it because it has a mean entropy of only log t. So we cannot say such a thing for any specific extractor, but rather what we can do is actually this selection of these green blocks that are close to uniform. This is actually another random variable that is supported over x. So that is the definition that we formalize, and we show that we can actually construct such multi-instance randomness extractions using Hadamard code or Reed-Muller codes. The constructions here are very standard constructions, but it's our analysis that I think is more interesting to the community. Okay, so with this multi-instance extractor, what can we do? There are a couple of things that we can do. First of all, we show that it immediately gives us multi-incompressible SKE and PKE. That corresponds to the incompressible encryptions for multiple users. Here, actually, it's very straightforward. First of all, we define what multi-incompressible SKE and PKE means. We give a simulation-based definition, and in fact, we show that if we just simply replace the seeded extractor in all of these constructions with a multi-instance randomness extractor, and pretty much you don't need to change anything else, it immediately gives you the multi-user case of these incompressible encryptions. So that's really just, you just need to plug that in and everything is good to go. So that is what we show as an application of the multi-instance randomness extractor. Along the way, we also discovered some additional results. First of all, as we imagine that we're having multiple users, it also makes sense to consider if we're among a single pair of users, instead of sending one single message between them, they could potentially send a whole bunch of messages between them. We observed that it is actually not possible if you have a fixed secret key size. With a fixed secret key size, it is not possible to support an unbounded number of messages between the same pair of users. Rather, we can only support up to a bounded number of messages between the two users. And we show how to actually adapt the constructions on the previous page to actually allow for these bounded multiple ciphertexts between the same pair of users. Additionally, we explore possible constructions under the random oracle model. So in the random oracle model, what we've shown is that you can actually construct a incompressible SKE and also incompressible PKE for an unbounded number of users, as well as unbounded number of ciphertexts between the users. And our constructions achieve optimal key and ciphertext sizes. And here it's interesting because it essentially says that public key tools might not be necessary to construct a multi-user incompressible SKE. So to quickly summarize our result, from the title, there are two parts. First part, there is the multi-instance randomness extraction. So that is the extractor that we define and we've shown how to construct. So that is one of our technical constructions. And the other part of the paper is mainly focused on how we can use such a multi-instance extractor to construct these multi-user incompressible encryptions. And we think this multi-instance randomness extraction could be of individual interest for other applications. Thank you.
Thank you. We have time for questions. Okay, if you don't have any questions, let's thank the speaker again. The next talk is on the paper titled Efficiently Testable Circuits Without Conductivity by Mirza Hadbeg, Subradeep Chakraborty, Stefan Zimbowski, Malgosia Galashka, Tomasz Lizure, Krzysztof Pichak, and Mirza will give the talk.
Hi, thanks for the introduction. So I'll be presenting our work, Efficiently Testable Circuits Without Conductivity. So this paper concerns tampering, which has been a subject of a lot of cryptographic work and also for the hardware security. The setting we are considering is, suppose you have a circuit which gets manufactured, and then while it's being shipped, an adversary tampers with it. And then when you receive it, you want to know whether it has been tampered or not. And you don't want to open up the circuit and look at it in an invasive way, which is, well, invasive, also costly. And so you want to basically check it by doing just input-output checking. And since the input space could be large, it's not efficient to do it on all inputs. And also if, so now if you do in a very restricted set of inputs, but the circuit is suppose like a SAT instance, a hard SAT instance, then even if the adversary tampers only the last wire, it might be hard to check just by looking at the output. Right? So the previous work which appeared in the ITCS this year, we defined this efficiently testable compiler, which takes any circuit C and then compiles into another circuit C hat, along with a small set of test instance, such that the number of inputs and outputs are increased a little bit, which would be constant. And these two circuits are essentially functionally equivalent, which is if we input the C hat with X with some padded zeros and just restrict the output to what the original output of the length of the original circuit, then they're basically same. Another property they have is this efficiently testable property, which is that for any tampering from certain class, I will define what class we consider, that if for on some input, these two circuits would have behaved differently, the tampered circuit and the honest circuit, then we can check it by actually inputting only from the small test set, right? And the previous, yeah. So the circuit model that we're considering is Boolean circuits with AND or XOR and NOT gates. And the tampering model that we're considering is that the adversary is allowed to tamper on all wires, and it can tamper them by either setting it to 0, setting it to 1, uh, or toggling, which just flips the if it's 0 to 1 or 1 to 0, or to do nothing. The previous work achieved efficiently testable compiler for all circuits with only constant blow up in the size, and the test the set of test input was also constant, right? You just needed to check on a few very few inputs to see if the circuit has been tampered. But a key limitation was something called conductivity assumption. So what is conductivity assumption? It's that so if there is a gate with a large fan out, and if you want to apply, if the adversary wanted to apply a tampering on that wire, then it has the same, the error propagates through all the wires. Right? But this may not be a realistic assumption for just for intuition. If one side of the wire is cut, then it's always 0, while on that other side, the adversary can apply any kind of tampering. So we model this by but basically putting a copy gate in there, and then the adversary is allowed to tamper all three. So yeah, all three of these things independently. Okay, so the question was, can we get this ETC without conductivity? The previous paper, the construction completely breaks down if you do not have this conductivity assumption. So the so in this paper, we wanted to answer this. Unfortunately, for the same notion of ETC, it doesn't seem to be possible. So we had to allow for two relaxations. So we had to allow basically for randomness. And then the tampering notion was to detect it. It's the same notion, except that the detection probability is now constant instead of, well, it's a smaller constant than 1, right? Previously, it was 1. So what the main results we achieve is that we have efficiently testable circuit compiler for all circuits with a constant blow up again. And the number of additional inputs is a little of n, output just like basically constant. And the randomness required is also a little of n. And you don't have too many queries. And for some concrete parameters, if you have like some 2 to the 32, the size of the circuit is 2 to the 32, you still need only 482 additional inputs, and the number of queries is like less than 200, and still we get a success probability of 1 by 32. Okay, so how do we get it? So just I'm going to define how this compiler outline works. So first we compile the circuit into a gate cover set. I will come to what gate cover means in a later slide. And then we notice still there is some problem, so we need like a compression to reduce the number of layers, and then we can recursively apply this compression to get the final circuit as desired. Okay, so coming to the gate covering set. So what the gate covering set is, it's a small set of test inputs such that every gate in the circuit has all 4 combination of values from the, so a gate like an AND gate will have both 0 0 as inputted or 1 0 1 1 0 1 as shown in the picture. And to achieve this, we need to add some extra gates. We add first like few inputs called disk control bits, and we can also add this extra XOR gates in appropriate places. And this can be done by a single pass algorithm, which goes through the circuit topologically and then adds the XOR gates at appropriate places. So once we achieve this, we can see this key observation that on inputs from the test set, can be either the output will be wrong or there will be information loss on some wire. And what does information loss means is that the wire, So any wire is said to have information loss if there be two inputs, x and x prime, on which their value in the honest circuit should have differed, but in the tampered circuit, they're actually same, right? And this information loss, we can detect it by just from inputs from the test set. Right? So if our test set is small, we can simply input all the possible values from the test set and see if the honest, what we expected as honest value came up or not. And this way we can check the tampering. So like naive first attempt is to just copy out all the wires, and then if you have information loss on some wire, then the yellow wires, like the copied out wires, the information loss persists on them, right? Because none of the tamperings can change. Once you lose the information, you cannot recover it. That's basically the idea. But this obviously has a problem that this has too many outputs, so we need to somehow compress it. And to compress it, we use this inner product gadget, which basically takes all these wires and inner products them with a random string. And then we get like basically one output. This requires too much randomness, so we need additional tricks to reuse the randomness. So we have a short length of randomness, and in interest of time, I will not get into those details. Please check the paper for those things. But eventually, what we need to also prove that once you have this information loss on these yellow wires, right, and that it persists through the compression layer. And the lemma we prove is that if there is tampering, if there is information loss on a wire, then it will show up after the compression layer with a probability of at least half. And by this way, just by testing on this small test set, along with some randomness, we can actually detect whether there's been information loss or the output is wrong, and this way we can check whether there has been a tampering. So few open problems which will be interesting to see in future would be, so I mean we discussed a restricted set of tamperings, right? Simply wire tamperings, but larger class of tampering attacks, maybe gate tampering, maybe something even bigger than that could be more interesting to see. Or generalizing the circuit model. So in our circuits, there's no state, or we are just considering Boolean circuits, so one could consider stateful circuits or arithmetic circuits. And further interesting thing would be if we can find some applications beyond hardware testing and tampering, say in like pure theory. That would be great. So thank you.
We have a lot of time. Questions? Yeah.
Regarding open problems, you use randomness. Do you know that this is necessary?
We don't have a proof, but we think it's necessary.
Okay, so that's technically an open problem.
Technically open problem, yes.
Any other questions? So a question. So in terms of tampering, are there other models that people have used, or like, or tampering as well as leakage? Like, these are probing kind of attacks, right? Your wire probing.
Yeah.
Are there other things people have considered recently about, you can read information about multiple wires?
I don't know about recent, like
Or
the hardware community discusses a lot of tamperings, but theirs are a bit different. But like noisy tampering, for instance, like noisy versions of tamperings would be, it's more realistic rather than where it's persistent forever. But like instead, okay, it shows up at some time with some probability. That'll be interesting. But yeah, it presents its own technical challenges of trying to prove things results and that kind of.
Okay. All right. Let's thank Mirza again.
Thank you.
And now we're on to the last talk of the session on immunizing backdoored PRGs. The paper is by Marshall Ball, Evgeny Dodis, and Ellie Golden, and Ellie will give the talk.
Hello, thank you for the introduction. So yeah, this is immunizing backdoored pseudorandom generators. This joint work with my advisors. So I'll begin by saying, what is a PRG? I'm sure you all know, but PRG is a deterministic function which takes in some uniformly random seed and produces a longer pseudo-random seed, which is going to be indistinguishable to a truly random seed. And what this means is that if Patrick is walking along and he sees a pseudo-random seed, he's going to think, oh, that's definitely like a random string. And so in this work, we're going to work with an online variant of pseudorandom generators, which are theoretically equivalent, but practically a bit more relevant. In an online pseudorandom generator, it's going to output its pseudorandom output over the course of many rounds. It's going to take in as its initial state some small uniformly random seed. And each round is going to output a new state as well as some pseudorandom output. And taken all together over the course of many rounds, the output should be pseudorandom. So in practice, pseudorandom generators are very useful. But people in the real world generally don't write their pseudorandom generators themselves. So where did they get them? And usually, how most companies work is they trust somebody who's written some pseudo-random generator standard and published it online, maybe with a proof of security, and they'll use it, say from SpongeBob. And most of the time, SpongeBob is a pretty nice guy, so this has no problem. The pseudorandom generator is all good and all secure. But what happens if, say, SpongeBob were to be evil? So evil SpongeBob may, when coming up with his algorithm, store some information about how he came up with the algorithm that will help him plant a backdoor into the PRG, which may give him some advantage in distinguishing it from uniform. And so a bit more formally, we define a notion of backdoored pseudorandom generators where, or there is the notion of backdoored pseudorandom generators where the output of a backdoored pseudorandom generator should satisfy two properties. It should be publicly secure. That is, Patrick, if he sees the output of a backdoored pseudorandom generator, should think, oh, that's a uniformly random string. But evil SpongeBob with his backdoored key, when he sees the output of a backdoored pseudorandom generator, should be able to open up the backdoor and tell, oh, this definitely came from a PRG. This is not random. So in fact, backdoored pseudorandom generators exist. And this has actually happened before in the real world, although it's a long story I'm not going to get into here. But the main question of our work is how do we actually prevent against these backdoors? So one kind of simple solution is that you could just build your own PRG from scratch. But unfortunately, most programmers are not cryptographers, and so they're very bad at this. And so this is pretty dangerous. Another solution you could do is you could re-randomize the public parameters or the randomness that's used in coming up with the algorithm. But when you're just given like a description of an algorithm, you don't really know necessarily what the public parameters are, and so this is not always going to be possible. So to solve this problem in a cleaner way, Dotis et al. In 2015 defined a notion of a immunizer. An immunizer is going to be some function that takes in a backdoored pseudorandom output and turns it into a cleaned up immunized pseudorandom string that no longer has a backdoor. And in particular, an immunizer F is going to take in as input one output from a round of a pseudorandom generator. And if you apply it in a non-line fashion, then you should immunize the pseudorandom output. So in particular, if Patrick sees the output of the immunized pseudorandom generator, this should look to him to be uniformly random. And also, if evil SpongeBob, who has the backdoor key, sees the immunized output, this should still look to him to also be uniformly random. That is, evil SpongeBob is sad against an immunizer because now his backdoor key is useless. One more thing I want to say about this notion is that the same immunizer F should work for any backdoored PRG. That is, if F is an immunizer, it should work for the PRG with pseudorandom output with the red backdoor, or with the purple backdoor, or the yellow backdoor, or even the blue backdoor. Dotis et al. Also shows how to construct these things. They show that a random oracle that has a salt, for which the backdoor is not allowed to depend on the salt, is a immunizer. And also they show how to build immunizers from something called universal computational extractors, which is a very, very strong cryptographic primitive, which we don't really know how to build from standard assumptions. So there are two kind of major flaws with these constructions and with immunizers in general. So you can show that immunizers of this form cannot possibly be made deterministic. They have to have some seed that the backdoor does not have access to. And we also don't know how to build these from standard model assumptions. And so a major focus of this work is going to be to try and remove the flaws from this primitive. And we do this by generalizing to something we call a 2 immunizer. So a 2 immunizer is going to take as input, instead of just one backdoor pseudorandom string, it's going to take in 2 backdoor pseudorandom strings. And so you can think of these pseudorandom strings as maybe 2 different runs of a single backdoored PRG on 2 different uniformly random seeds. And just like an immunizer, a 2 immunizer is going to take these 2 strings and move it and turn it into a pseudorandom string without any backdoor in online fashion. So in particular, 1 round of a 2 immunizer will take in the concatenation of 1 round of both pseudorandom backdoored strings. So the more focused question of this work is, can we build 2 immunizers that are simple and deterministic from standard assumptions? Why do we think this is possible? Well, we will turn to look at the backdoored random oracle model, which is somewhat similar. So a backdoored random oracle is a random oracle where the adversary gets arbitrary information about its truth table. And prior work gives some pretty strong evidence that the XOR of 2 backdoored random oracles is a random oracle without any backdoor. And because a backdoored random oracle is like a very, very idealized notion of a backdoor, we would hope that this result would also translate to our setting of actually backdoored PRGs. So we provide 3 different results. Our first result is that, unfortunately, XOR is not going to be a 2 immunizer in our model. And there's an asterisk here because we rely on some cryptographic assumption, but it's a standard model assumption. And second of all, we show that a random oracle is a 2 immunizer, and it is in fact a deterministic 2 immunizer. So this gives some heuristic instantiation of a 2 immunizer. And finally, we give very strong evidence that it's very hard to build immunizers in the standard model, either 1 immunizers or 2 immunizers. So the first result is that XOR is not a 2 immunizer. And before I get into this, I'm going to talk about a very simple way to build backdoor PRGs from something called pseudorandom encryption. Pseudorandom encryption is, I guess, what you would expect. It's just an encryption scheme where ciphertexts are pseudorandom strings. And what this means is that to the public who doesn't have access to the private key, any ciphertext is going to look like a random string. But to the person with the private key, they can decrypt ciphertext and get back the original message. And note that this, on its surface, already sounds a lot like a backdoored PRG, and it's very easy to build backdoored PRGs from pseudorandom encryption. How you do it is that Evil SpongeBob will publish as its algorithm the public key of the encryption scheme. And then to run the PRG, parties will just encrypt 0 under this public key. Pseudorandomness of encryption shows that this is a publicly secure PRG. But Evil SpongeBob can distinguish outputs from random just by decrypting and see if you get 0. So how are we going to now show that XOR is not a 2 immunizer? Well, what we'll do is we'll build a backdoored PRG that cannot be immunized by XOR. And in particular, we'll consider what happens if the ciphertexts are somewhat homomorphic in a way. Homomorphism is maybe the wrong word, but it's the best word I could come up with. So what I mean by this is that the encryption, if you take 2 encryptions of the same message under the same public key and you XOR them together, you should get something that's also an encryption of that message under that public key. If you have an encryption scheme that satisfies this property, then the XOR of 2 encryptions of 0 is also going to be an encryption of 0. And this means that for the backdoored PRG that just outputs an encryption of 0, you're not going to be able to immunize it by using XOR. And so if there exists any encryption scheme that's pseudo-random and satisfies this homomorphism property, then XOR is not going to be a 2 immunizer. And in fact, it's not hard to show that such a scheme can exist based off of learning parity with noise. And so we show that assuming some variant of learning parity with noise, XOR is not going to be a 2 immunizer. So our second result is that a random oracle is a 2 immunizer. And I'll give a quick sketch of the reasons why, but maybe not go too much into the details. So the main reason is that no party of the game can actually query both inputs to the random oracle at the same time. And the intuition behind this is that the output of each pseudorandom generator has to be unpredictable unless given the seed, even if you have the secret key. And otherwise, it's not going to be publicly secure because people can just test if there's a collision. And no party is going to have access to both seeds at the same time, not even the pseudorandom generators themselves. And that's kind of the whole key idea. Our final result is that there is evidence against a standard model immunizer. And what do I mean by a standard model immunizer or standard assumption? I'm going to be talking about falsifiable assumptions or efficiently falsifiable assumptions, which are just assumptions that can be expressed as a cryptographic game with an adversary. The main, as a preliminary, let me talk about what a black box reduction is. So a black box reduction is just going to be a way to prove that some protocol is secure. This is a pretty common method. And how it works is you take some adversary for your protocol, and you show how to, in a black box manner, generically transform it into an adversary for some falsifiable assumption. And so therefore, if the falsifiable assumption holds, then that means that your protocol will be secure. So our third result is to show that you cannot use this proof technique to show that any two immunizer is secure, regardless of what falsifiable assumption you're working with. And since most security proofs are at their heart black box reductions, this shows that it's fairly hard to actually show security of any two immunizer. Note that there's some caveat here that the immunizer must be highly dependent on its inputs, but this is a fairly natural restriction, and most immunizers that you can come up with would satisfy this, like inner product. In addition, we also show the same result for one immunizers, and here we no longer need the caveat. So I'm going to end by talking about something I like to call the Venn diagram of crypto. So in cryptography, there are primitives that practitioners like and primitives that theoreticians like. And in particular, stuff like public key encryption, pseudorandom generators, or collision-resistant hash functions. We know how to build these very efficiently, so practitioners are happy. And also, we need to know how to build these from theoretical assumptions that seem all secure and whatever, so theoreticians are happy. However, something like indistinguishability obfuscation, we know how to build from theoretical assumptions, but we have no clue how to really do this in a practical way that practitioners would be happy with. And the same holds for something like fully homomorphic encryption or anything with a quantum output. But on the other side of things, there are cases where practitioners are happy and theoreticians are not. For example, SNARDs. We know how to build these from in the random oracle model and can do this in a way that has been used in practice, but there's no satisfying standard model constructions. And in particular, there's a similar black box separation. So I guess the main result of this work is to place immunizers also in this practitioners happy box. In the sense that we give a heuristic construction of an immunizer just by using a random oracle. But we also show that it's pretty hard to build these from any standard model assumption that theoreticians would be happy with. And yeah, thank you for listening.
Thank you. Any questions? Okay. Do you have a question?
Yeah, sure. For snarks, there's recently been some progress on replacing the random oracle with correlation intractable hash functions. Have you looked at that at all? Whether the same approach could apply to immunizers, or are we pretty sure that it wouldn't?
We didn't look at correlation intractable hash functions in particular. I guess there's not really the same kind of Fiat-Shamir type thing here. The previous result looks at universal computational extractors, which is kind of somewhat more standard model, but we don't really know how to build it in the same ways. But yeah.
Any other questions?
What kind of random oracle do you use for the proof? Particularly, do you need programmable random oracle, or maybe non-programmable would be enough?
We don't. I don't think we need programming for the random oracle. And in fact, we also do this in the auxiliary input random oracle model. So there's several levers back. I suspect that maybe you can even do this without programming in like the backdoored random oracle model, but we didn't show this.
Any other? Okay, so then let's thank the speaker again and all the speakers of the session. Now we have a coffee break.
you can move to the title slide. So, but how do we present it? I'll just wait for the Shulchan. I will just use guys. Okay. Yeah. And this is mine. This for me. Yes. Okay, so we have just enough time for a brief introduction before Zvika starts his talk. So it's a great pleasure to introduce Zvika Polkelski. We'll speak about when the universe speaks in quantum crypto. Zvika is a professor at the Weizmann Institute of Science. He's made breakthrough contributions to the theory of cryptography in many different areas, very famously in the study of fully homomorphic encryption and quantum cryptography, also obfuscation, verifiable computing, and many more. He's a recipient of the Blavatnik Award for Young Scientists in Israel, of the Gödel Award, and the Fox Test of Time Award. And I'm sure I'm omitting some other awards from this list. So we're very lucky to have him. Looking forward to his talk. And without further ado, let's welcome Zvika.
Thanks, Guy. Hi, everyone. Well, thanks for being here. Thanks to the committee for inviting me and for the organizers for organizing this great conference. I would like to start with some personal words. It was really hard for me to prepare this talk, and not because of the contents of the talk. As you may know, we had in my country, in Israel, there was a bit less than 2 months ago, an enemy invaded our country and literally sent death squads to murder families in their homes, and moreover declaring that they want to do it over and over again, no matter what. So that's very unsettling. So I made a talk. Hopefully it'll be educational and also entertaining. There's jokes and everything. But I do want to remind there's still a cloud over this this whole thing. So I will start the talk now. Thanks for bearing with me. So the talk is going to be about quantum cryptography and the universe. So I'm going to start by talking about quantum cryptography. So quantum cryptography is doing pretty well. So TCC 2009 was my first TCC. And there was one quantum paper there out of 33 papers in the conference. This year I checked, I found 6 quantum papers out of 68. So both in number and in ratio, we're doing pretty well. And in crypto, there's a similar phenomenon. And in general, I feel like quantum computing is becoming bigger and more mainstream, both in the TCC and general theory of computer science communities. It used to be that when someone gave a talk about quantum computing, they'd have to spend time introducing the model and so forth. And at this point, I think most people sort of know at least the basic guidelines. Talking about my own personal experience, I took a class in quantum computing back in undergrad in 2001 with Dorita Aronov, who actually sort of did a very good job at sort of giving us the right intuition or approach on how to think about quantum systems. So that was great. I'm not sure how much of the technical content I remembered, but still I felt that I knew what was going on. So I went to these, the quantum sessions that were like usually the last session in the conference and very low attendance, and tried to sort of figure out what was going on. And things are very different now. I think, things are much more mainstream. And you may wonder why. I don't really have an answer. You could guess that maybe it's related to the advances in actually constructing quantum computing devices, which gave rise to things like the NIST post-quantum cryptography competition, trying to construct cryptographic primitives that are resilient to quantum attacks. There's probably some feedback loop there. So that's probably something that brought quantum computing back more to the attention of people. I also think that maybe there's like a bunch of brilliant students that were looking for cool hard problems to work with. And quantum computing is like a great playground. It has a lot of interesting and important problems that sort of brilliant researchers can sink their teeth in. I should mention before moving on that most TCC and theory of computer science works in quantum computing still work in this model of fault-tolerant quantum computing or fully scalable quantum computing, which is not what the machines that are currently built are implementing. So there's still a way to go. So this is still sort of forward-looking research, and at least in terms of sort of being able to actually implement it. But nevertheless, these are sort of important problems. And I'm sort of coining this term quantum TCC to refer to those quantum questions that we, the TCC community, care about. So it's not necessarily papers that are published in TCC, but it's the papers that it's the problems that TCC people would care about. And in recent years, we've seen a lot of progress and multiple fronts on this quantum TCC. And I'm just going to sort of briefly go over a few of them, but the talk is going to be sort of very focused. But I didn't want to just go without mentioning them. So one thread is to work on post-quantum cryptography, which is classical cryptographic primitives that are secure against quantum attacks. So you can think about cryptographic assumptions, you can think about building blocks, you can think about proof systems or protocols. And there's a more basic question of how to model security in the presence of a quantum attacker. So for example, rewinding becomes an invalid technique, at least out of the box, and there are other challenges. So there's a lot of work that's done there, how to work in the random oracle model. The other thread I wanted to talk about was what happens when you actually want to use quantum communication. So protocols that actually use quantum communication. And again, you can ask all of the questions that we're asking in the classical world, also in this world where you're also allowed quantum resources. The third bullet here is something that actually has no real classical parallel, and that uses the properties of quantum states that they are unclonable. So we're going to talk about it a little bit more later, but essentially you cannot generically copy a quantum state. And this means that you can actually use this property for cryptographic purposes. Most notably, quantum money relies on this unclonability property. There's works on quantum copy protection, certifiable deletion, all sorts of tasks that you sort of have no hope of doing in the standard classical model, but you can do quantumly. There's a thread of work on delegating quantum tasks. So this is the case where you have a classical party that wants to utilize a quantum party. So you want to delegate a quantum task while you yourself are classical. So there's questions of security and questions of privacy. So you can think about certifying quantum computation. You can think about certifying generation of randomness, which is a task that quantum devices know how to do. You can think about protecting your privacy in the process and so forth. And you can also think about the foundations of quantum cryptography. So all of those basic questions, what does it mean? What does one-wayness mean? What does pseudorandomness mean in a quantum world? This is also an area that has seen a lot of progress recently. But today, we're going to talk about quantum gravity, which is not exactly on this list. In particular, how cryptography comes up when thinking about the universe. And the way that I want to do this is by actually starting by talking about a few ideas from the foundations of quantum cryptography. This is also going to remind us a little bit of the model, and then I'm going to relate them to things that are going on in quantum gravity. So let's do it. Let's start by talking about quantum pseudorandomness. In particular, I want to talk about quantum pseudorandom states that were introduced by Ji Liu and Song. So the idea there is to create a pseudorandom quantum state. So let's start by talking about what quantum states are. So a quantum state, an n over n qubits, so an n qubit quantum state, is defined by 2 to the n dimensional complex unit vector. So you can see it. Oh, let's try this. Good. Okay. So you can see that that phi here is a vector, and it has 2 to the n coordinates. It has 1 coordinate for every classical configuration. So we have n qubits, which is the sort of quantum system that corresponds to n classical bits. So for every configuration of n classical bits, we actually have a coordinate in this vector. And each of these coordinates has a coefficient. So you have a 2 to the n dimensional complex vector here. And this is the quantum state. How about now? Good. I'll do both. So we said that it's a 2 to the n. Okay, that didn't work. So we said that it's a 2 to the n dimensional vector, so it contains a lot of information. It contains an exponential amount of information. But actually, this phi only contains n qubits. So you can only really extract n bits of information out of this. And perhaps sort of most famously, you can measure this quantum state in the standard basis. And then you're going to get as an outcome an n-bit classical string. And you're going to get the value x with probability that is the absolute value of cx squared. But there's other ways to process this quantum state, but you're still not going to be able to get more than n bits of information out of it. And so what does it even mean that it has an exponential amount of information if you can only extract n bits out of it? So really, if you want to extract, you can recover more information, but you need to have more copies of this quantum state. So instead of just giving you, n qubits containing this quantum state, I can sort of give that to you, and then give you n additional qubits that store the exact same state. And I can do it again and again and give you t copies of this quantum state. And this will allow you to extract sort of t times n bits of information about this sort of exponentially long vector. So in that sense, the quantum state is sort of well-defined, even though you can only extract n bits out of it every time. So this sort of hints to two properties of quantum states. One is that information extraction is in general a destructive process. Otherwise, I could have sort of extracted n bits and then extracted a little bit more. But in general, that would destroy the state. And the second thing is what I alluded to before, is that quantum states cannot be, in general, duplicated. So there's this famous no-cloning theorem. And essentially, if you could, then you could have just, I could have given you one copy, and you could have copied it and extracted more information. So these are sort of basic properties of quantum states. Now, what is a random quantum state? Well, it's just taking this exponential dimensional vector to be uniform over the unit sphere. That's all. And that has a lot of entropy, like an infinite amount of entropy if you want to be most general. But even with finite precision, it has an exponential amount of entropy. And again, if I give you exponentially many copies of the state, then you can extract it. Now, what is a pseudorandom quantum state? So that's what you would think. It's a low entropy distribution, so it can be generated from a polynomial seed efficiently in such a way that the quantum state that you get is indistinguishable from uniform, even if you're given polynomially many copies of this quantum state. So it can be an adversarially chosen number of copies, so long as it's polynomial, and should still be indistinguishable from this other vector that has an exponential amount of entropy. Okay, so JLS, who sort of proposed this idea, had suggested quantum money as one motivation, and also that these pseudorandom states can model sort of the ground state of generic physical systems. They also showed a construction from one-way functions. So essentially, giving us the sort of construction from the weakest possible crypto assumption. Well, not so sure. So we're used to thinking of one-way functions as the weakest assumption that is necessary essentially for cryptography. And where's Iftach? So shout out for Iftach's talk 2 days ago. At least in most cases, we think that one-way functions are essential. And this was semi-formalized by Pagliazzo and Luby. So if this is the most basic cryptographic primitive, then is it implied by this notion of pseudorandom states? So it's enough to think about a little bit to figure out that probably not. These notions are sufficiently different that they should not, that pseudorandom states should not imply one-way functions. It's not so easy to prove, but it was proven using a quantum oracle separation by Kretschmer. So we know that at least in some formal sense, pseudorandom states are not expected to give us one-way functions. But what does this mean about the role of one-way functions as the minimal cryptographic assumption? Well, you could think that maybe pseudorandom states are not actually crypto, because if you think about the motivations that I mentioned in the previous slide, we talked about quantum money and sort of modeling quantum systems. So maybe pseudorandom states are only good for quantum tasks, and they cannot help us in getting classical cryptographic tasks. Turns out this is not the case, and actually you can do cool classical cryptography just with pseudorandom states, and this was shown very recently. My focus is going to be on bit commitments. Because quantum bit commitments are actually, very also classical, but quantum bit commitments are a very interesting primitive with many properties that supersede what is known classically. So, and they're very useful for many applications. So, in particular, in the quantum setting, you can take any commitment protocol and turn it to be completely non-interactive. So you can have you can even have non-interactive, statistically hiding commitments, which is something that is just not possible to do using just classical communication. It also implies a bunch of other other crypto primitives that we think of as being pretty strong, like oblivious transfer, which in the classical world is not implied by commitment schemes. You can also use, so what I'm talking about here is actually quantumly committing to a classical bit. So this is it's a classical task, and we're performing it using quantum resources. But you can also think about committing to quantum states, and you can also do this using classical commitments. So commitments are kind of cool. You can also show that in the quantum world, the existence of commitment schemes, of bit commitment schemes, are actually equivalent to this new primitive that we defined that we call EFI. And EFI is just a pair of distributions over quantum states, which are efficiently sampleable. They're statistically distinguishable, so they're statistically far, but they're computationally indistinguishable. So this is a very basic primitive. It's just distributions that are computationally indistinguishable, statistically far. In the classical world, this is equivalent to one-way functions. In the quantum world, this is equivalent to commitment schemes. And we don't know what is the relation to other primitives, but at this point in time, I think that we do not know of any how to achieve any cryptographic task computationally without also getting EFI. And this is due to recent result, like the last hole was plugged by Korana and Tomer in a paper that I think was posted just 2 weeks ago. This is sort of the evidence that we have, but we don't have like a sort of a formal reason yet as to why, if and why this would be essential. And we don't know of a separation from pseudorandom states. We know there's a derivation in one direction, but we don't know what's going on in the opposite direction. So we can do cryptography even if one-way functions do not exist. This is great. The next thing that I wanted to talk about was pseudorandom unitaries. I'm just going to mention it briefly, mostly for the sake of the open problem in the end. So you can think about pseudorandom quantum states, but you can also think about pseudorandom quantum operators. And quantum operators are unitary operators in general. And just as you would want a quantum state that's indistinguishable from a random quantum state, you could want to get an efficiently computable quantum operation that's indistinguishable from a random unitary. And there are candidate constructions, but there's none with a proof. So we don't have a proof under any assumption. So that's a very good open problem for the brilliant young or not young researchers and students that want to work on it. The next thing that I want to talk about is pseudo-entanglement. In this case, we take our quantum system and sort of split it into two parts. So we have two subsystems, A and B. Each one of them has n over 2 qubits. And entanglement is these quantum correlations between these two subsystems. And entanglement is a very fundamental notion in quantum information and quantum computing. Almost all the applications that we have use entanglement. If you want spooky interaction at a distance, you need entanglement, and many other tasks, Shor's algorithm, but really almost everything, teleportation. The most basic entangled system is this very simple EPR pair. So this is a 2-qubit system, and it's just sort of a superposition of the all zero state. So it's over two qubits. So it has two parts. Each one is 1 qubit. And it's a superposition of like the all zero state and the all one state. And this state is maximally entangled, which means that it has the most entanglement that it can have. I'm not going to go too deep into what this means, but I just want to mention this monogamy of entanglement property, which means that if two states are maximally entangled with each other, then they cannot be entangled, each of them cannot be entangled with any other quantum system. So this is a useful property. Now, there are many ways to quantify entanglement, which is not a good thing because for every application, you need to figure out what works for you. A popular one is to use entropy. So you can use the negative of the conditional entropy between the two subsystems, A and B. And this entropy measure that we use is the von Neumann entropy, which is a quantum extension of Shannon entropy. Notice the minus sign. So if systems are entangled, then this von Neumann entropy can be negative. And this means that the systems are actually entangled. So negative relative information, relative entropy, means that the two systems are entangled. And physicists refer to this von Neumann entropy as entanglement entropy. Well, yeah. Good. So the task of pseudo-entanglement is to create systems with low entanglement. So systems where they have subsystems A and B that don't have much entanglement with each other, but are computationally indistinguishable from ones with high entanglement or even maximally entangled quantum systems. And you can show that you can do this using pseudo-random states or other techniques. So there are actually works that show this, and we'll see why this is interesting. I want to mention like a recent work where we tried to consider a different notion of entanglement measure. We want to think about sort of operational pseudo-entanglement. So rather than sort of looking at this, I don't know what to call it, analytic notion, you're actually thinking how many EPR pairs do you need in order to construct this sort of bipartite state AB. So A and B start by just sharing a bunch of EPR pairs, and then they work locally and they can communicate classically, and you need to create a quantum state. How many EPR pairs do you need in order to complete this task? And you can also think about the opposite task, entanglement distillation, where you start with your state and try to get, by local operations, as many EPR pairs as you can. And you can define pseudo-entanglement with respect to these measures, and sometimes this is also interesting. Okay, so let's move on to applications. Anybody knows what this is? Right, it's a black hole. So this is a Sagittarius A star, which is the black hole in the center of our galaxy, the Milky Way, for those of you who are from different galaxies. Do you know why it's called Sagittarius A star? What the star stands for? So as far as I understand, when astronomers come up with an exciting discovery, they mark it with a star. So A star just means that it's an exciting, radio source or whatever it is. So, astronomers they have, I guess, thousands of years of experience in naming things. So they're probably pretty good at this. So that's a cool naming convention. So yeah, we're going to talk about black holes. But before that, a little bit of a disclaimer. So, I'm a TCC person, just like you. I'm not a physicist. So this means that if you there's a bunch of physics questions that I'm not going to be able to answer. But the good thing is that I'm going to be able to give us sort of our perspective on these matters. So I'll do my best. So what I want to talk about is first is black hole radiation and complementarity. So let's see what that is. So let's start by talking about black holes. We've seen a real black hole, but here's an illustration, which is, I think, at least as nice. So in classical gravity, which is general relativity, so a black hole is just a region of space-time. This is true still also in the quantum regime. So we used to think, some people are used to thinking about black holes as an object, but it's not. It's just a region of space-time where if information gets in, where whatever goes in there, any information that goes in cannot come out. You can schematically think about the black hole as having a singularity in the middle. So there's like very strong gravity in the singularity. You don't want to go in there. And the boundary of the black hole is called the event horizon. And this is essentially the line where if you cross it, you can never go back. And the region of the event horizon doesn't necessarily have very strong gravity because it can be very, very far from the singularity if the black hole is big. So this is how you should think about it. Like around the event horizon, things seem normal. If you go too close to the singularity, and an illustration of a book going into a black hole, but information goes away. It goes into a black hole, it never goes back. However, I think pretty surprisingly at the time, in the late 70s, Bekenstein and Hawking actually showed that black holes should emit radiation. If you analyze sort of the region of the event horizon quantumly, then you see that radiation is supposed to come out of it. It's called Hawking radiation. And this means that the black hole is going to evaporate eventually. So it's if you just take a black hole and leave it be, it's going to start radiate and radiate and radiate until after like gazillions and gazillions and gazillions of years, it's going to evaporate. This is very weak radiation, so we cannot measure it. So we only have theoretical evidence that it exists, but I think everybody's pretty sure that this is actually like something that happens. And now you already have a conflict with general relativity, because general relativity says that nothing can come out of a black hole, but actually, radiation does come out, and in the end, the black hole is going to evaporate. So what happens to all the information that goes in? I think the consensus now, or near consensus, is that the information is going to come out eventually. So the entire evolution of the universe is unitary, and therefore information at the level of the universe, information never gets lost. So if it goes into the black hole and the black hole radiates, then the information is supposed to come out in some way. And now we need to think about this information in the Hawking radiation and what its properties are once we establish that in some sense it has to contain the stuff that was thrown into the black hole. So naturally, it's not just going to be like the black hole throwing the book back at us. It's going to be encoded in some way, and the encoding actually matters. And I should mention that usually the way black holes are modeled as, so it's known that black holes are supposed to mix information very rapidly. So information that goes into the black hole sort of gets smudged all over very quickly. And it's actually usually modeled as a random unitary, but we know that it can't be a random unitary because the universe, well, it should be computationally efficient. So this sort of brings us back to this notion of pseudorandom unitaries that I mentioned before. Pseudorandom unitaries could be like also interesting in the study of how the real implementation, how the universe really implements black holes. So that's just leaving it out there, and it's an additional motivation. So again, thinking about the entropy that is contained in the Hawking radiation, so we already sort of try to think, we're inclined to think that it's encoded in some hard way. So one thing that physics tells us, or tells the physicists, is that any information that's emitted in the radiation should be entangled with information that remains in the black hole. So that the radiation that goes out is actually maximally entangled with other piece of radiation that actually goes back into the black hole. So what goes out needs to be maximally entangled with the stuff that's inside. On the other hand, it should also be entangled with all the radiation that was emitted previously. So if the black hole is old, then it means there's a lot of radiation that's already come up, that already came out sort of in the history of the black hole. And once the black hole gets small enough, there's no sufficiently many degrees of freedom inside the black hole to be entangled with everything, so it needs to be entangled with the outside. And that's a problem because we mentioned the monogamy of entanglement property. So a quantum system cannot be entangled with two different systems. So you cannot have the outgoing radiation being maximally entangled both with the inside of the black hole and with the outside of the black hole. So that's a conundrum. And it was solved it's attempted to be solved in a very creative way. So they're saying, well, you know, you seem to be entangled with two things. One of them is inside the black hole. One of them is outside the black hole. They're sort of pretty disjoint from each other. So maybe they're just not two different things. Maybe it's just the same thing. It's two manifestations of the same sort of quantum system. And if you're inside the black hole, then you see it in one way. And if you're outside the black hole, you see it in a different way. But actually, it's the same thing. So it's mind-blowing, but not as mind-blowing as we will get. So this is sort of a prominent idea on how to handle this sort of radiation paradox.
Can I ask a question, Zvika?
I don't know. It depends on the chair.
Yes.
Okay, then I'll ask two.
You already wasted.
Wait, I didn't approve to.
I don't. First of all, I don't understand why does it have to be pseudo-random and not random? Why can't the universe be truly random? I missed that.
Oh, because truly random just has exponential complexity, just like in the classical world, right? You don't expect real random functions to exist just because they have an exponentially long description. If the universe is efficient, I mean, you know, it needs to be polynomial in the length of the history of the universe.
So you believe the Church-Turing thesis for the universe?
In this room we do.
Okay, and my other question, if it's two manifestations of the same system, is that related to cloning? Is it like?
Right. So you can think about monogamy of entanglement and no cloning as very related to each other. So you could think that you actually sort of clone that you can also think about it's a violation of no cloning, even though it's not like you're taking a generic state and cloning it, but it's fine. It's a very similar intuition, so it's good to think about it in this way. Okay, good. But we want to talk about cryptography. So let's see what happens next. So Al-Mihiri et al. Actually were not satisfied with this answer, and they actually proposed an experiment where one can actually sort of see this monogamy of entanglement. So the whole point is that these two things are the same system, so you should never be able to sort of witness the two copies side by side. And they proposed, so this firewall paradox is not really a paradox, it's a thought experiment. And what they're saying is someone sits outside, it looks at the history of the radiation, it takes out of it, it like sort of computes out of it the piece of information that's supposed to be entangled with the next thing that's supposed to come out. It sees that you're fully entangled with this thing that comes out, and then you jump inside and find like the black arrow that matches, and then you see that these two things are actually you witness this violation of the monogamy of entanglement, and this is not good. And therefore, they suggested that Event Horizon maybe should have this firewall, which is a very high energy barrier that prevents these black holes from existing. But I think a lot of physicists don't like it because they really want to think about Event Horizon as an area that is sort of tame. It doesn't have high gravity. There's no reason that firewalls should appear there. So they really want to try to salvage this sort of complementarity without using firewalls. And Harlow and Hayden had the following proposal. They were saying, look, in order to conduct this experiment, you actually need to take this historic radiation and decode it. And that could be a computationally hard task. And then they gave some toy model where decoding the radiation is SDK hard. And Aronson showed that you can actually use injective one-way functions. So you can actually use cryptography to create like toy decoding problems that are hard. And bam, problem solved. We don't need to worry anymore about the firewall paradox. Except like, this, how is that even a thing? That sounds crazy, right? Like, there's an experiment that could in principle happen, but we're saying that because it takes a lot of computational resources, then we can just disregard it. The point was that if a sufficient amount of time passes in the decoding process, then the black hole will evaporate, or this black arrow is going to reach the singularity and be out of our reach, or something is going to happen that's going to save us from actually seeing this violation of monogamy. But this really sort of hinges on us sort of being unsuccessful, like taking a long time in running this decoding task, which seems unsatisfactory, but it's actually not very foreign to the way sort of the physicists think about these things. So they have this invention that's called effective field theory. So they realize that they cannot sort of get a theory that works at all energy scales. So they can come up with these field theories that work in regions that have fairly tame gravity, and they can come up with pretty accurate theories that actually sort of say everything that's going to happen there, but they actually tell you nothing about what happens in high energy, like in high gravity or something like this. The theory is not going to say anything about it. And this is a good thing because it allows you to sort of analyze these regions without having a theory of quantum gravity. But it's also a bad thing because you want to learn something about quantum gravity. It also means that if you don't get to these high energies, then you're not going to be able to learn anything about quantum gravity. And the universe didn't have to be this way, but it appears that at least in some cases it is. So they're pretty okay with saying some things you can have a theory that works very well, but when extreme things happen, it just stops working, and that's fine. Like sometimes the universe just hides from us what happens when extreme conditions happen, and then they're saying, okay, so solving intractable problems in less time than you're supposed to should also count as outside the regime of applicability of this effective field theory, and then maybe it's okay. So this is their rationale. So this is sort of a way that I think it's still considered a way to resolve this paradox. Very recently, we were able to show that actually it's not only that you can use sort of cryptography, like injective one-way functions, in order to create these hard-to-decode systems. There's actually an equivalence. So if you define the problem properly, having, like, again, a toy black hole that creates radiation that is hard to decode is actually equivalent to the existence of quantum commitments to classical bits, or these EFI pairs that I was talking about. So if we have these quantum commitments, then we can create hard to decode black holes, which is good. It's similar to what was known before. But actually, the opposite is also true. So if there exists like black holes that asymptotically emit radiations that is hard to decode, then you also have quantum commitment schemes, which I'll talk about a little bit more later. But just sort of the basic idea. So in hindsight, it seems a fairly natural connection because the black hole sort of emits this information. The information exists inside the radiation. It's fully determined, but it's inaccessible. So this should remind you of a commitment to this quantum information. So the black hole really, whatever it emits, it has to be a commitment to this quantum to this quantum value, this quantum information that is being emitted, and we can get quantum commitments from classical commitments. Quantum commitments to quantum values from quantum commitments to classical values, and this is sort of what we do here. But this sort of brings us to a more philosophical question of whether we can sort of try to use this sort of things as getting some additional justification to the existence of cryptography. So why do we think, so usually when we think about cryptographic assumptions, why do we think that they're hard? Well, you know, we rely on our intuition, insight, experience. A lot of people tried to factor for a very long time and weren't successful. So why don't we sort of think about this as a cryptographic assumption? If we're lucky, we also have this win-win paradigm that, you know, if it's not, then we have a new algorithm. So that's a good thing. But you can think about an alternative approach, sort of very naively and schematically. So first, map out all the laws of nature. So do science and figure out exactly how the universe works. And then, you know, find a process that sort of can be carried out efficiently, but is hard to invert, and use that as your one-way function. So again, so this is very naive, but you can try to do this. It's somewhat different. It's not going to give you like a proof, because whatever model you have, whatever laws of nature you have, it's just a conjecture. You never know that it's actually the real laws of nature. But it's different somewhat from the previous approach in terms of methodology, because in order to deduce the laws of nature, you do experiments and you do observations, and this is at least sort of a different path from the way that we normally think about creating cryptographic assumptions. So this sort of black hole thing is, you could think about it as an example, sort of, even though it's all like thought experiments and not experiments you can actually conduct currently. But it can give you some sort of independent evidence. So it's a different path that shows that cryptography could actually exist. So I think that's pretty cool. Of course, it's debatable. Good. So I want to actually give you another example of where cryptography is used to save complementarity. And this is the ghost in the radiation. So this is a paper by Kim Tang and Preskill. And they were thinking about another aspect of this complementarity thing. So we're saying that the stuff inside and the stuff outside should actually be the same system. So if I want to communicate with someone inside the black hole, can't I just do it by sort of communicating with the radiation? So sort of you can think about the ghost of the person inside the black hole actually living in the radiation, and you can maybe interact with them. And that should not be doable. But again, sort of the approach that they take is to use pseudorandom states to argue that anything that you do to the radiation, you cannot do anything meaningful to the radiation that will sort of affect in a meaningful way what's going on inside in the system inside the black hole. And so they showed one direction. While I was preparing the slides, I realized that there's an open question here, whether you can show, again, sort of an equivalence, that it has to be the case, that it maybe, you know, more pinpoint the cryptographic object that you need here. So that's another angle on this. Okay, and I want to switch to the next thing that I wanted to tell you about. So this was black holes and where cryptography comes up in that regime. Now I want to talk about holography and the ADS-CFT dictionary. Okay, big words. Let's see what those are. So what is holography? Holography is this principle that says that everything that happens sort of inside some region is in some sense determined by the boundary. And actually this phenomenon also happens in black holes. We didn't talk about it before, but you can actually think about all the information of the black hole actually being concentrated around the boundary. It's well known that, in terms of physics, it's well known that the entropy of the black hole is proportional to the surface area of the black hole and not to its volume, which is, you know, so holography is counterintuitive, right? If you think about a black hole, it has some volume. And if you want to try to sort of pack information, like let's say I want to have some region with some volume, and I want to try to pack information into that region. So I'm just going to take like a bunch of hard drives, and I'm just going to sort of, you know, put them one next to the other in this thing, and this is going to scale according to the volume of the region. But it turns out that if you try to like squeeze things as much as you can, in the end you're going to sort of create a black hole, and you can actually not store more information than the surface area of the boundary of the region. because a black hole is the region, has the maximal entropy of all possible regions in space-time. So this is just to say how holography is sort of sometimes counterintuitive principle. It sort of collides with our notion of locality, that things should only affect what's near them and not be affected by like something that's happened on the outside. But it's a hot topic. And in particular, there's this ADS-CFT correspondence that was introduced by Maldacena in '97. It's probably the most researched concept in high energy physics. I think I checked, the paper has like 24,000 citations. Yeah, everybody works on ADS-CFT. And now we will know what it is also, at least in broad terms. So we consider a universe. Why not? Why not consider a universe, right? That's what we do all the time. And this universe has ADS geometry. ADS means anti-de Sitter. This is like hyperbolic geometry for those of you who are differential geometers, which I'm not. But it has some geometry, this anti-de Sitter geometry. And for such a universe, you can actually sort of describe them as like this cylinder. So at every slice in time, you can put this anti-de Sitter space into like a circle, and then you have time evolution, and the time evolution actually creates this cylinder. So the cylinder is the universe. And if you think about the cylinder, then it actually has a boundary, like the surrounding of the cylinder, and this is a conformal boundary. For us, it's just a name. So the inside of our universe, it's called the bulk, and that's the universe with gravity. So it's so in classical physics and general relativity, gravity corresponds to curvatures in space-time. So the inside, the bulk, is allowed to have this has this curvature. But the boundary actually has this flat geometry, so there's no gravity on the boundary. And why is that a good thing? Well, this ADS-CFT correspondence, so CFT stands for conformal field theory, and it says that if you want to do physics with gravity in the bulk, like you have a physical theory that describes what's going on, like a quantum gravity theory of the bulk, then it's going to be dual to some physical theory on the boundary that does not have gravity. So CFT is conformal field theory, so you have a conformal field theory on the boundary, and this one does not have gravity. So I think in the original Maldacena paper, this was shown for some string theories. So again, it's a theory. It can be shown in some models. I don't know how far it can be extended. It's also worth pointing out that our universe does not seem to have ADS geometry. But why let that stand in our way? It's still a cool property that allows physicists to study quantum gravity. So why not take advantage of it, see what we can learn from it, or they see what they can learn from it. So the hope is that to do physics without gravity is potentially easier. This is something that physicists know how to do pretty well. So you're just going to do this physics without gravity on the boundary. You're going to derive from it the physics with gravity, the quantum gravity theory in the bulk, and bam, you solve quantum gravity. We can all go home. So this is a pretty nice plan. They do need to figure out first what is the correct CFT theory that lives on the boundary, and then also how to translate from the states and operators that you can apply on the boundary to the states and operators that live in the bulk. So the point is that if you want to run an experiment in the bulk, you should be able to sort of maybe translate it into the corresponding state of the boundary, run it or do your calculations on the boundary, and then translate it back, and then you'll know what happens in the experiment in the bulk. So it's challenging. There's a lot of work that's being done to try to better understand what is going on there. And here, actually, cryptography spoils the party a little bit. So we can think, so there's various ways where crypto can spoil the party. I'm going to describe like this general template. So think about the following thing. On the boundary, think that you can have two different states, psi1 or psi2. So you can think about a boundary that has psi1 or a boundary that has psi2. And let's think about the geometry on the ADS that you have that corresponds to these boundary states. So each one of them corresponds to potentially a different geometry. But geometry is something that you can see sometimes. So you can have an operator like measuring tape that you can use in order to sort of distinguish these two dual geometries, right? So you're just going to go and measure and see if you're the first one, then you're going to do one thing, and if you're the second one, you're going to do something else. And this will allow you to distinguish these two geometries. And again, you have the inverse dual mapping. This means there's also an operator in the CFT region that has these properties. So why is that a problem? So it could be a problem if we have certain conditions. So first of all, we want to if we can generate these psi1 and psi2 such that they're computationally indistinguishable. Let's say computationally indistinguishable even to quantum computers. But they're still legal CFT states. So not all states are legal. I guess there's a whole theory behind it. But there should be legal CFT states. And yet the geometry they induce is different and can be distinguished sort of in the bulk, in the ADS part. If this happens, then you seem to run into a problem, right? Because somehow quantum gravity allows you to distinguish between these two states. Because what you're going to do is you're going to go to the ADS. You're going to use your measuring tape, and this is going to tell you whether your boundary state was the first one or the second one. So this gives you a distinguisher between these two possible states. So if you can generate such states, then this sort of quantum gravity could allow you to solve intractable problems and violate the quantum extended Church-Turing hypothesis. So quantum extended Church-Turing means that anything that can be computed in the universe can also be computed by a quantum computer. So yeah, that could be a problem. And one way to go is to say, yeah, well, quantum gravity maybe is a new computational model. Maybe we have a new tool now, and we need to learn its complexity and so forth. But the more pessimistic and probably more realistic point of view is to say that in order to construct this distinguisher that I was mentioning, you actually need to be able to compute these mappings, the mapping between the either in one direction or in the other direction, or both. You need to be able to compute these mappings, and probably this is what's computationally intractable. So all these things can be true, but still, if this dictionary, the mapping between ADS and CFT is hard, then the quantum Church-Turing hypothesis is not broken. But it's tough luck for us, because like this whole way of trying to do physics by working on the boundary and then mapping it into the bulk might have a problem to actually be useful. Like if you actually want to use it, you might run into like hard computational problems. And yeah, that's a conundrum. So it's important, interesting to see whether this can actually happen. And I think people think that it usually should not happen. Like if your ADS geometry is like nice, then things should also behave nicely on the boundary. But in some cases, it could be the case. So there's this work by Boland, Pfefferman, and Vazirani that sort of relate. So now they're using pseudorandom states, but they work really hard to show that you can actually come up with a construction of pseudorandom state, or at least conjectured construction of pseudorandom states that can actually be generated in the CFT on the boundary. So whatever people think of the boundary, it allows you to generate these pseudorandom states. And they're related via some conjecture to some surface area of stuff that's going on inside a wormhole. And in that regime, they're able to sort of show that in some cases you're going to have high complexity of the dictionary, or breaking a cryptographic assumption. The works that I mentioned before in pseudo entanglement are also related because again, sort of the, I guess, widely believed conjecture is that surface area in the bulk is actually related to the entropy of the corresponding region in the boundary. So if you have a region in the boundary and the quantum state on this has some entropy, this is actually going to determine the volume or the surface area of some section, properly defined section in the bulk. So studying pseudo-entanglement is sort of, again, a way to try to sort of tap into cases where you'd have states that are computationally indistinguishable, but correspond to different geometries, in the bulk. So this is a little bit, the first work is more sort of inclined towards this goal. And finally, I just wanted to say that in order to conduct this experiment, it doesn't necessarily mean that we need to live in a universe where ADS-CFT holds. It's quite possible that we can think about an imaginary universe that has ADS-CFT correspondence, but so long as we can simulate this universe, right? So long as we can, in our universe, sort of simulate this ADS universe and see what comes up there, we're still going to be able to generate a distinguisher. So it's possible to sort of argue. So it's meaningful to argue about this, even if this is not our universe. I'm going to wrap up. Yeah. So good. Good job, everybody. Quantum TCC rocks. Everybody's doing a great job. We have like great achievements, and we're going in very interesting directions. We're creating privacy and security tools for this quantum future. At the same time, exploring the mysteries of the universe, coming up with interesting ideas and observations. That's great. We're not done yet. There's more work to be done, both conceptual and technical work. And we need to do it. So thank you very much.
Thanks a lot, Zvika. So we have time for some questions.
So you assume that the black hole dynamics is pseudo-random unitary. So if you already have pseudo-random unitary, this also implies EFI, and pseudo-random unitary is stronger than EFI. So why you want to construct EFI?
So if I understand the question, so in this black hole, the hardness of black hole decoding, we don't assume anything about the black hole dynamics. So all we're saying is that if the black hole dynamics, whatever it is, creates a hard to decode radiation, it can be a pseudo-random unitary, we don't know. You're right that if we understand the black hole dynamics, then maybe we don't need this correspondence because we know exactly what is the radiation that is emitted. But we can say, even if we don't know the dynamics at all, if it emits radiation that is hard to decode, then it gives you a commitment scheme. And if there exists a commitment scheme, then at least it's plausible, or at least it's possible, at least in some toy model, there could exist a black hole that emits a hard to decode radiation. So, it doesn't excuse us from actually studying the black hole dynamics. It just says that we can sort of try to speculate some of its properties even without knowing what the dynamics are.
So hardness of decoding is weaker assumption than the pseudo-randomness of black hole dynamics.
I think so. I mean, I didn't think about it thoroughly, but from our little discussion, I would think that you can say that. Yeah.
Thank you.
Okay. I'm gonna let Guy manage it.
Yeah. So you were saying that somehow like this black hole theories give us, if they're correct, they should give us cryptography. Do like the specific proposals of how black holes work give us candidate constructions of commitments and cryptographic schemes? Or?
I like the question. I'm not sure what the answer is. So this is actually sort of to relate to the previous questions, right? If you're doing something that's pseudo-random, then it makes sense that it's going to give you something that's perhaps not very satisfying. It's not clear if it needs to exactly be a pseudo-random unitary because there's no place for the seed, right? Like all these pseudo-random objects actually have a seed. And in like, if you think about black hole dynamics, then you're supposed to know all the laws of nature. So I don't know where's the place where you plug in the seed for this pseudo-random unitary. So I don't even know how to frame this model. But yeah, I think it's a very interesting sort of direction to try to study.
Okay, so you mentioned the relation with the classical one-way function primitive. What about what do we know about the relation with the classical P versus NP question?
Okay, so there's this, I think, a whole different branch. It's not different, but there's this whole branch of trying to understand how one should think of quantum complexity theory. And again, I'm not like a super expert, but I can tell you sort of my angle on it. So it seems like there's a lot of a lot of quantum tasks that cannot be reduced to a classical parallel. So this sort of the complexity class hierarchy, even quantum classes like QMA and BQP, they still think about deciding a language or computing like some classical function. And when you're talking about quantum functionality, then it's not clear that like all of this structure is even suitable to study these things. And there are some ideas on sort of how to define classes where you have quantum inputs or quantum outputs. In particular, one important open problem that I didn't mention here is whether EFI exists even if P equals P space. So we know that in this case, like if P equals P space, then P equals BQP. So that's fine, but it still doesn't resolve the question of whether you can have quantum cryptography. So was that the question?
Yeah. Thanks.
Yeah. I had one question. You said, I think at some point, and I may have completely misunderstood this, but that basically you cannot manipulate, sort of, if we think of our black hole as a pseudo-random generator, we cannot manipulate the output by feeding more things into the black hole. But I think you also said that sort of the black hole's computation or the seed is sort of just polynomial in the length of the universe, or whatever has been fed in the past. So even if I feed in something, like that is, if I take as long as if I wait as long as the lifetime of the universe up to now and feed in, like, if I double the amount of information that is in the inside the black hole, I still cannot manipulate things or manipulate the output or bias the output.
So I was talking about like a very the simplest scenario, which is that nothing goes into the black hole. Stuff only comes out. So that you take a black hole and let it radiate. I think there are some thought experiments and suggestions on trying to sort of get to more interesting circumstances by putting things inside and seeing what happens. Was that what you were referring to?
I thought you had some slide where you said I cannot manipulate the output by feeding more things inside, but I may have misunderstood.
Yeah. So maybe it wasn't clear. So what I was talking. Okay. So this was the ghost and radiation slide you're talking about.
Maybe.
Okay. So let me say again something that I did say. So you can say if you have complementarity and the outside and the inside are the same thing, and let's think about sort of your friend going into the black hole, or I don't know, not friend. Going into the black hole to explore, then you might want to then you may be able to communicate with them by sort of interacting with the radiation that's already outside. And what this work of Kim Tang and Preskill says is that you should not expect to be able to do it if you're an efficient process.
Last question, I think.
So so we think of simulation as a thought experiment, right, for security definitions. So is there any reason to not have simulation which is not physically realizable, right? A simulator lives inside some black hole which can violate non-cloning and so forth. Would it make sense to think of that?
So violating no cloning, it's not that, okay, so this no cloning thing, it's not that it's like, it's an operator that's not permitted. It's actually, it's not even well defined in quantum information theory. So it's just something, but I think you were saying something, you were referring to something somewhat different. So you're saying I can just write down this.
Yeah, you can copy the entire state. You can.
Sure. Yeah. If I actually write this exponentially long state on paper, then I can clone it in the sense that I can take this classical description and copy it. So long, if I have like a classical description of what's going on, then I can sort of copy it, but it's still not going to allow me, to duplicate a physical system.
So I guess my question is there a safe way to define like an imaginary world where in some boxes, quantum physics is all violated, but still it's good enough for our thought experiment to say this is secure, right?
So yeah, so I think you can. I'm saying that you need to be careful because like the frame of reference really matters. Like it's not physical. It's not a physical process like cloning, but you can say that under some again definition of like a classical description of the system, what do you mean by duplicating quantum state? Right? It doesn't feel like a very satisfying answer. We can talk about it later if you want.
Yeah, let's thanks Vika again.
Thanks.
And we can all talk about black holes over lunch. I think it's in the usual place, I think.
Hi, there are a few codes that has been inadvertently left at various places, and they are currently at the registration desk. And for your information, and the broadcast to everybody that says we have spare conference kits for available is on like the people who have registered but did not get a conference kit has priority. So enjoy lunch.
All right. Welcome everyone to the session on lower bounds. We have 5 great lower bound papers. And the first paper studies the foundational question of the communication complexity of fine-grained key agreement in the random oracle model. And Guangzhou Yang is going to give the talk.
Hello everyone, I'm Guangxu Yang. This is my first time to attend a conference, so I'm honored to be here. Today, I'm going to talk about the communication neural bonds of king agreement protocol via density increment arguments. This is a joint work with Min Huang, Xinyu Mao, and Jiapeng Zhang. We are from University of Southern California. First, I introduce the definition of king agreement protocol in random oracle model. That is, there are 2 players, Alice and Bob. They share a random oracle, and they can do some queries to random oracle and communications. After communication, Alice output king A, Bob output king B. For correctness, we hope that king A equal to king B with high probability. And there is a third player called attacker. He can see the communication transcripts and query the random oracle. For security, we hope that any attacker see the communication transcripts and make a few queries counter guess the key. So here is a simple protocol called Moco-Pado as an example. In Moco-Pado, Alice uniformly sample x1 to xl and query the oracle to get fx1 to fxl. And Bob also uniformly sample y1 to yl and query the oracle to get fy1 to fyl. After they query the oracle, Alice just send the oracle answer to Bob, and Bob will check if there is I, such that fyj equal to fxi, and send the fyj to Alice. At the end of communication, Alice output king A is xi, king B is yj. So for correct this, you will set n equal to 10 times L squared, then Alice and Bob will have common queries with high probability by Butler paradox. And if M is large enough, then K equal to King B with high probability. For security, since the attacker can only send communication transcripts, so giving a fyj, he should make at least omega L squared queries to find x such that fx equal to fyj. In fact, recent paper proposed a variant of Moco-Pado achieve perfect combinations and same security. Perfect combinations means that king A equal to king B with probability 1. So Moco-Pado only prevent a quadratic gap between the efficiency of the horned party and the attacker. So the question is, can we do better? Here is some negative results. The first result shows that any king agreement protocol where Alice and Bob make L queries can be broken by the attacker with L to the power of 6 queries. There is a technique called intersection query, simulated Alice and Bob to do some queries. And this result improved to L squared queries. And this result implies that Moco-Pado is optimal with respect to the query complexity of the attacker. And they use a technique called heavy query. Intuitively, heavy query is that the attacker query the positions which queried by any Bob with high probability based on his knowledge. So heavy query has wide applications in different areas and focus on black box separation and the power of random oracle in a secure two-party computations. So private results don't consider the communication conversation between Alice and Bob. And as we know, the amount of communication bits between Alice and Bob is also important in practice. For example, if we consider Moco-Pado, Alice and Bob need to exchange omega L bits. So the question is, can we do better with the same security and this communication? Here is a conjecture by recent paper. They conjecture that any L query and C-bit communication agreement protocol can be broken by the attacker with CL queries. This conjecture means that Moco-Pado is also optimal with respect to communication complexity. So non-adaptive means that Alice Bob query is fully determined by their internal randomness. So as a partial result, they also prove the two-round case. That is, any SQL query and CB communication, the grammar non-derivative two-round protocol can be broken by the attacker with CL queries. And they also use a technique called heavy query and analysis the communication cost via a hog technique. And analysis the communication cost means that to bound the number of heavy queries. So let's turn to our contribution. Our contribution, we prove the conjecture for perfect companies. Perfect companies means that king A equal to king B with probability 1. So our result implies that the protocol in recent paper is optimal. Compared to previous technique, we also have some technical contribution. First, we propose credited queries. Intuitive related queries are not only heavy, since we consider the communication cost, so we should consider the query also highly correlated to the communication transcripts. So we analyze the communication cost via a simple technique called the density increment argument. This means that we can bound the number of correlated queries by a density increment argument. Let's turn to definition of correlated queries. Correlated queries means that we see the S is correlated, means that the FS the condition randomness IRB and the private queries giving a transcript the retrieval loss is large. So based on correlated queries, we propose an algorithm for the attacker. The attacker is very simple. Just query the correlated queries until with set L and until low correlated queries, and update their knowledge after each correlated queries. And at the end of algorithm, they output the majority of what possible output. So given this algorithm, we have two steps to finish our theory. The first step is we need to show that the algorithm will succeed with high probability. The second is that we should bound the number of iterations by communication complexity. We finish it by a technique called density increment argument. Density increment argument is a powerful technique in combinatorics, but I think it's not known in cryptography. So density increment argument defines a density function to record the change of the view. So we prove this number. The expectation number of iteration of the algorithm is bounded by communication complexity. So first, we reveal that at the beginning, the density function is phi tau implicit and is updated after correlated queries. By chain rule, we show that the density function decreases at least epsilon in the expectation after epsilon correlated queries in each iteration. And we also notice that the density function is always non-negative, since F is uniform distribution if you only condition on randomness and private queries. So by the combine the two factors, we will have that the expectation number of iterations you give a transcript is phi tau implicit over epsilon. And if we take the expectation over the transcript, we will give our results. So here is a summary on our proof outline. The proof outline is as follows. First, we give an algorithm that the attacker queries the correlated queries in each iteration and output the majority of all possible output. And the number one is that we bound this number of iterations is communication complexity. It is proved by density argument. And number two is that we show that the success probability of the algorithm is large. This is proved by rectangle view in communication complexity. So we omitted the proof network. So last, I discussed some open problems. I think the first open problem is how to extend our perfect companies to imperfect companies. For our technique, we can't fix the transcript. We should consider the communication round by round to achieve imperfect companies. And another question is how to achieve adaptive protocols. And for this open problem, we have no idea right now. And the last open problem is that since heavy query has wide applications, so that's the open problem is that whether our correlated queries also have applications with respect to communication complexity. So that's all. Thank you.
Questions? Maybe one question. Can you explain where you use the perfect Lopez assumption in your proof?
We use it in the rectangle view. So our results really we should analyze the transcript rather. Another transcript is respond to a left rectangle, and we found some structure in the left rectangle based on the perfect company's property. So if you want to consider imperfect companies, you should do it round by round, not fix the transcript.
Well, thank you. More questions? All right, if not, then let's thank Guangzhou again.
Okay.
All right, so the next talk studies the foundational question of the difference between the security of sponge hash functions and Merkle-Darmgraph hash functions in the preprocessing model, and Guangxi Duan is going to give the talk.
Thank you. My name is Xiaoqi Duan, and today I'm going to talk about the time-space trade-off for collision finding in sponge functions. So let's start with the domain extension hash functions. You should be familiar with this. That is, it is a hash function that will take a long message for input, and it will still come out with a very short hash value. That is to say, if we have an input, we can divide it into B blocks, say M1 to MB, and we can apply this function f on the first block of message M1, and we will get an intermediate value. And with this intermediate value, we can combine it with the second block M2 and apply the same function f again to get another different intermediate value. And we can repeat this for all the B blocks and finally get an output. So this is the domain extension hash functions, and there are many applications like the famous SHA-2. It uses the Merkle-Darmgraph hash functions. So in this setting, the function f can be seen as a random function. And another very famous setting is at SHA-3, they used sponge hash functions. And the different thing here is that in sponge hash functions, the function f can be viewed as random permutation because for efficiency reasons and practical reasons. So the difference here is that the adversary should also have access to f-1 because f is a random permutation, and also because this has been widely used in reality to have both access. And also, as usual, our target is that these functions should be hard to find collisions with them. So maybe you will ask, because in SHA-3 there's an extra thing that we have the access to f-1, is it possible that SHA-3 is somewhat less secure than SHA-2 in some sense? And the answer is somewhat yes in the following model. That is the so-called auxiliary input model. The intuition of this model is that what if in reality the adversary have some extra knowledge about the function used before? For example, if the function have some backdoors, he may use this information to design attacks more generally. So the setting of auxiliary input in model is that it is very similar to the random oracle model, except that the adversary will have the S-bit extra information about the function f. And with this information, he can also, as usual, make T queries to the f or f-1, and he will try to output a collision. And usually the trivial birthday attack also still applies because actually, you do not need extra information to perform a birthday attack. And in here, it is just t squared over n or t squared over r, where n and r are the function ranges in MD and sponge. But the interesting thing here is that except from this trivial attack, there do exist non-trivial attacks in this auxiliary input model. For example, we can look at the case for Merkle-Darmgraph that for different message lengths, that indeed have some different known attacks. For example, when b equals to 1, you can see that there is a term of s over n, where s is the s-bit information that we have in the AI model. So it does say that in this auxiliary input model, there are more things that the adversary can get. And this is true for almost all parameters, like there's a new thing that performs better than the per se attack. And this is for the Merkle dam guard. And the interesting thing comes in sponge, that is, you can have a look at this fancy thing when b equals to 1. So what I generally want to say is that if you treat, say, C and R, they are of the same order as N, you will find that the advantage of this attack is strictly better than the attack for MD. So what does it mean? It means that because the adversary have the access to the inverse function in sponge, it means he can really take use of this advantage of the inverse function and to design a better attacks that will outperform the original attack in Merkle dam guard. I would like to mention that it's heavily utilized the inverse oracle, otherwise this attack won't occur. So as long as this situation occurs, it will be interesting to say what is exactly happening in auxiliary input model. For example, what about the security upper bounds? And there are many research in this area. Some of the earlier research will use techniques like presampling and compression, but most recently, the technique used are so-called multi-instance games. We will talk about it later. And what we want to know now is that with the help of multi-instance game, we indeed can have some nice results. For example, in the case of Merkle dam guard functions, we can prove almost tight bound for almost many parameter ranges, except that this when b is larger than 3 and smaller than t. And this is still open now, but the thing is that multi-instance technique, it works pretty well here for giving us this upper bounds in the AI model. But again, things become strange when we come to sponge. Actually, we actually do not have tight bounds for all the short collisions when b is smaller than t. So more specifically, these upper bounds, you can have a look, for example, when b equals to 2, in the current upper bound proved by multi-instance games, there's a strange, say, s squared t4 to the c squared term. This term do not occur in any attacks and do not occur in some other analysis. So maybe you will try to think if it is the problem of the multi-instance game technique itself. For example, it will introduce this somewhat strange parameter. And also, is it that we haven't utilized the full potential of multi-instance games, and can we prove potentially better bounds? And our first result shows that indeed for b equals to 1, we can utilize the multi-instance games technique more thoroughly to prove an almost tight bound. And we also simplified the proof for b equals to 2, although we didn't give better bounds. But there's almost everything we can do. So our next result states that why is it the case? Actually, we have already found the corresponding attacks for the multi-instance games such that the given bounds matches the current upper bounds we have proved by multi-instance games. So it generally means that if we want to continue to shorten the gaps between the upper bounds and lower bounds, probably we shouldn't rely on this multi-instance games technique. Okay, we have been talking about MI for a long time. Let's go into more details about them. So the reason why we would like to use multi-instance games is that we have this good theorem states that we can reduce an auxiliary input adversary with some success probability to epsilon to a multi-instance game adversary with probability epsilon to the s. So the idea is simple, is that you already have an AI adversary, but you do not know the advice piece, so you can just guess it. You have 2 to the minus s probability to guess it correct, and if you guess it correct, you can have the winning probability epsilon almost in each round, so we can, the probability will just be amortized into this exponential factor. And more precisely, what multi-instance game does is also very similar to the random oracle model. For example, it has of many stages. At the beginning of each stage, it receives a challenge, and it can make T queries to the oracle, and it needs to output the, say here, the collision. And here's the general picture that is for round 1, round 2 until round S. He will receive S challenge thoughts, and he will need to give different different outputs. And the oracle will check if this collision are indeed valid. And something to notice here is that it is very different to auxiliary inputs, that there's no longer the advice string. At the beginning of the first round, actually the adversary knows nothing about the function, and he need to answer and prepare correctly. But one thing different here is that the function f will not change in different rounds. So, and my adversary, what it can do is that it can utilize the information it has in the previous rounds. For example, in round I, he will already make, say, I minus 1 times t queries to the function f, and he may already have some idea of what this function looks like. And he can indeed use this function's properties to help him design, to help him find collisions in the current rounds. Although he needs to win S rounds to win the whole game, it is still possible for us to find some interesting things here. And the main idea for proving lower bounds via multi-instance techniques is we are trying to bound the success probability of the multi-instance game. And if we can do this, according to the previous theorem, we can just transform it to a corresponding upper bounds in the original AI adversary. And there are reasons why we'd like to use MI, because there's no advice Bs, and we can use many good techniques here, and it is often easier. So let's come back to our results again. So for B equals to 1, we examined the multi-instance technique more carefully, and combined with compression argument, we get an almost closed bound. Here, almost closed is that there's a similar gap between the function inversion that has this form of gap. So maybe it is hard to further close the gap. And we will not go into details, but the more interesting thing is that we already have some matching attacks in multi-instance games. For example, for B equals to 2, I mentioned that there's a strange S squared T force to the C squared term. And we already have find attack that has this specific winning probability in the multi-instance setting. So it just means that this is an inherent problem of the multi-instance technique itself, and probably we cannot use them to further bridge the gaps. To introduce this attack, we will first come back a formal definition of the sparse functions. So we have mentioned that it is a permutation from R times to C to R times to C. Here, R is actually the domain of our message, and C is our domain of the random source, or the so-called initialization vector. And we repeat B times to get a function. And what we are trying to do is that we are trying to find a collision in the multi-instance setting. And you can imagine of how can we find the collision is that we will try to start at a source and find two different passes. Here, when B equals to 2 means we only have two length passes, such that they will try to finally collide at some point. For example, if they share the same thing 0 here. So one thing we can hope to do is that, recall that we have the inverse oracle here. We may try to use this inverse oracle to query out many different thoughts that will finally collide at 0. For example, we will constantly query f minus 1, 0, I, and we will get different things like M1, C1, M2, C2, something very different. And this is the first half. And for the second half, for example, when we are given this challenge thought A, we will try to query different messages starting from these thoughts. And we're hoping that what if we can hit some previous thoughts that we have made before in the step 1. So what does it mean? If we can indeed hit a thought here, that is, we can have 4 queries of this form. The first query and the third query is what we have occurred in case in the step 1, and The second and the fourth are the queries in step 2. And if they can share the same sort A1, and it means we can design the messages properly in this way. That is to say, because we know they share the same message, share the same sort, we can design the message such that it just will go through the edges. In the previous one, we used the edges f-1, but here we will try to go through it from the positive way, such that the messages will indeed collide at the same sort. And you can have a check that if we have this thing, indeed, we can perform a valid collision in this way. And a short notice is that we can guarantee that we will meet enough number of different sorts, and the probability of hitting such two sorts will be large enough. And this is the general idea for the finding the attack. And here's some other attacks. So finally, for a recap, we have showed better bounds for b equals to 1 in finding collisions in the auxiliary input model. And we have showed that there are limitations of the current multi-instance technique. So it's interesting if we can have tighter bounds, or if we can find better methods, or even if we can find better attacks to close the gap. Thank you.
Questions? Then maybe I have one question about the kind of the difference between the security of sponge constructions and Merkle-Darmstadt constructions. Somehow in the beginning I was thinking, does this mean we should move back to using Merkle-Darmstadt hash functions in practice, or what does this mean? Because you emphasized the inverse oracle multiple times. I think, maybe you can elaborate.
Because it shows that in the auxiliary input model, maybe sponge functions are less secure, but actually in many cases, the adversary do not have this specific power like auxiliary input. So in general use, it should be okay, but in this specific scenario, it may have some problems.
Thank you. Questions? All right, then let's thank Rachi again.
Okay.
All right. So we now return to communication lower bounds, this time in the context of continuous group key exchange, and Miguel Gueto Noval is going to give the talk.
Hi, everybody. So I'm going to be presenting this paper written with Benedict Auerbach on the topic of post-compromise security and the upload cost of getting this notion of security for protocols called concurrent continuous group key agreement. So basically, let me start by motivating and contextualizing this paper. So basically, we're talking about group messaging, which is something that we are, or most of us, and actually billions of people around the world are familiar with, since this is offered by very popular apps like WhatsApp or Signal and many others. Communication in this context has an asynchronous nature because users may be offline, then maybe a few hours later they come back online. And also there is another property that is important to consider, is that these groups may remain active for a very long period of time. So here we have pictures, 6 users. So we are actually interested in the case of very large groups, end users. And here each user basically
communicates with the server. So it uploads and downloads some messages from the server. And we're actually going to distinguish between two kinds of messages. The first ones are the ones users actually want to send. So hi, maybe a picture, a video. And then there is another kind of message, which is the messages that are used to actually provide security to the users. And we basically want to study the upload cost, so how many messages have to be uploaded to the server in order to provide some notion of security to these users. More specifically, I'm going to be considering a primitive called continuous group key agreement, which basically supports group messaging by giving the users a way of agreeing on a key, maintaining this key over a long period of time, and it does so on a round-based way. So in every round, users agree on one key, and then they just use this key to send the messages I was talking about before. So a picture or a video, whatever they want to say. And then, as you can see here at the bottom, we have a tree on the left that we have for users. Its KI denotes a pair of public and secret keys. Users know the keys along their path, or at least the secret keys. Of course, they can know more public keys. And then it provides the possibility of doing updates. Here on the right, Alice is doing an update, changes the keys along her path, and just tells Bob, this is the new K5, and it tells Charlie and David by encrypting the new K7 under key K6. Oh, hey, this is a new group, the new key that we all agree on, and we're going to be using in this round. So, of course, it's a cryptography conference, so I'm going to be talking about security as well. So here there is an adversary that is given the possibility of corrupting users in every round. And the property we want is post-compromise security, which basically says if all corrupted parties have done sufficiently many updates since they were corrupted, we must have a new secure key. And the topic, so the last word in the title that I haven't really talked about is concurrency. And the question is, okay, in the previous picture, only Alice was doing an update, but what happens when we have several parties doing updates? Maybe actually even all users in the group. So here I have two different protocols that are like the two approaches to dealing with concurrency. The first one called propose and commit and used in a standard recently introduced by the IETF called TRICM. And the second one is COCO. So what has happened in the first picture in both cases, in which all nodes are red, is that the adversary has corrupted every single party. So right now, the adversary knows every single key in this tree. And then the subsequent pictures represent the next few rounds in which every single party is doing an update. And these updates are being done concurrently. So we see how the trees heal. And in the first case, after just 2 rounds, the key at the top is no longer in red. So it's a secure key. So it has achieved 2 PCAs. So security after just 2 rounds of updates, but it has done so at a high cost, actually n squared, because what happens in the last round is that party Alice has sampled a new path and then has encrypted the nodes along her path to the other parties. And if you actually look at the number of edges that reach one of the trees along Alice's path, there is a linear number of those edges. So basically, if this is done by all users, it has a cost of n squared. While if we look at what COCO does, COCO basically what happens that every user is doing just sampling the path, a new set of keys for their path, and sending this to its neighbors, basically, so the co-path, which means only a logarithmic number of ciphertexts is used, and it does so, and as a result, it requires more rounds to heal a logarithmic number of rounds because these are binary trees, and this is being done by all users. So we get a cost of n times log square n. So lower cost, but more rounds. So as I've just said, propose and commit has a worst case total update cost, so the cost of all users together of n squared. And actually, we know this is optimal because in 2020, Beanstalk, Dulles, and Rösler gave a lower bound in some symbolic model that shows that in the worst case, this is the best you can get. So we know it's optimal. And as I've said, in Cocoa, it was proven by giving a protocol that with more rounds, you can lower the cost. So the question we study in this paper is basically, well, can we get lower bounds for the case of this kind of delay notion of PCS, which we call KPCS, in case just the number of rounds you're willing to wait until you get security. And we also give upper bounds that are very close to this lower bound. And this applies to any protocol basically that is constructing from public encryption and pseudo-random functions. So as I said before, there was this symbolic model used by Beanstalk, Dulles, and Rösler. We also use it, though, for fewer cryptographic primitives. And in order to prove lower bounds there, what we do is translate that problem into a combinatorial problem. So on the left, I'm drawing a protocol, basically. So the actual keys are there. On the right, I'm going to be drawing the combinatorial problem that we actually studied. So, here all keys are safe, the adversary doesn't know anything. So we just put on the right a set associated to each of these keys that consists of the users who know the corresponding key. So in this combinatorial model, we have this set system that should correspond to the safe keys. We have a sequence of updates and a sequence of corruptions. Here, Alice was corrupted, so we just remove the sets that contain Alice from the set system. So the first picture captures correctness because there is a shared key, which is represented by the set of all parties being part of the set system. In this second row, we are saying this is actually the set system of secure keys because there are no sets that contain corrupted parties. And then in order to study communication cost, we must make sure there is a connection between the number of messages that are sent on the left when doing an update and something related to these sets. So we basically have Alice doing an update. This means the keys Alice knew, the new keys are now secure, so they're back in the set system here. In the set system here. Okay, thank you very much. And now we must make sure there is indeed this connection I was telling you about. So we do so by looking, for instance, at the set here A, B, C, D. And I'm not sure if you can know this, but it's written as a union of three sets. The first one is color in blue, which is the singleton of just contains Alice, which was a new key, just sampled by Alice. And then there are two more sets, singleton B and the set that consists of two parties C and D, which were already part of the set system. So we basically say, okay, Alice here on the left sent to ciphertext, which correspond to the dashed edges on the left, encryptions to K2 and the key K6. And those are exactly the sets color in black here on the right. So that's the notion of cost we are basically considering here, which indeed corresponds to counting ciphertext, which is exactly what Alice is going to be uploading, and therefore what we are actually studying here. Now I'm going to present to you the lower bound. So first, let me give you an idea of what's going to happen. So we start at time 0. So this is a timeline. The first round is just a setup. Then in the middle, there is going to be a round of corruptions. And then at the end, we want a secure key again. So what we say is no matter, so there is this kind of first, oh, sorry, I'm doing something incorrectly, I think. So there is this kind of get ready phase. So you can choose any sequence of updates before the corruption takes place. Maybe one that you think is very good to lower the cost in the future. Then what we say is, okay, there is still a way of finding a set of corrupted parties in this round here that corresponds to the vertical bar colored in red, and a sequence of updates for slightly more than k rounds that will make you have a total update cost of at least k times n times k root of n over log k. So now let's look at the statement slightly more formal. For the exact bound, which here does not include an epsilon, that is actually part of the actual statement of the formal one, which you can find online. So basically, we consider a small epsilon, and we are going to ask for security after slightly more than k many rounds, so 1 plus epsilon times k, and we give you this time to get ready. No matter how you do it, we are going to give you a set of corruptions and a sequence of updates that satisfies that every corrupted party will have done at least k many updates, and therefore you must make sure the key is secure, and the total cost over these healing rounds is going to be at least this expression here. And we also give a translation theorem that takes this bound in the combinatorial setting and gives you a bound in the symbolic model for any scheme that is correct, and keep KPCN secure and build only from public encryption and PRFs. Finally, let's compare this to the existing upper bounds. So before, we had already said that n squared was optimal for 2 rounds. This work basically for k equals 2 matches that. And we also give a product called CoCoLite, and it's just slight variation of CoCo that is up to log n factor matches the bound, the lower bound we got. So it's very close to the lower one we just talked about. It leaves the open question of whether we can overcome this bound by considering more powerful primitives, or maybe not asking for perfect correctness. Thank you.
Questions? Can you explain where your proof doesn't work anymore if you allow, say, dual PRFs?
Yes. So what happens is that basically, when we look at the picture here at the bottom, we are always talking about the cost at one specific round, and using dual PRFs or some other primitives, maybe you can delay this cost over several rounds. So basically, the ciphertext is sent in one round, but it doesn't really correspond to when the user learns the corresponding secret. So that's where the translation between symbolic and combinatorial, at least this combinatorial model, kind of breaks.
Thanks. Any other questions? Okay, then let's thank Miguel again.
Okay, can you see my slides and my screen?
Yes, we can see your slides and your screen. Excellent. Okay. Then, the next talk is about new lower bounds and new lower bound techniques and relation between new lower bounds and the generic group model. And Charlotte Hoffmann is going to give the talk.
All right, thanks. Yeah, so this is about our paper, generic group lower bounds via reductions between geometric search problems. And this is joint work with Benedict and Guillermo. So when we consider the hardness of assumption, sorry, one second. When we consider the hardness of assumptions in groups, we usually consider the setting where we have some problem in a group G, and then an adversary that gets as input the description of the group. And it also gets as input some instance, for example, a group element here, and it needs to produce an output. So in this example, this would be the discrete log of the group element. Okay, and now cryptographic schemes, they rely on certain assumptions that problems like this are hard, but in the standard model, there's no way of proving that this actually holds. So if we want to find some evidence of hardness for those problems, we need to move to idealized models. And one example of such an idealized model is the generic group model. So here we restrict the access of the adversary to the group. It does not get the description of the group as input, but there's an oracle that knows the group, and the adversary can interact with this oracle. One example is Shoup's generic group model. So here the oracle has a random labeling function L that assigns a label to every group element. And then the adversary only ever sees labels of group elements. And when it wants to perform a group operation, it sends the labels of two group elements, for example, here A and B, and then the oracle responds with a label of the addition or the multiplication of those group elements. Another example is Mauer's generic group model. Here there's no labeling function and no labels, and the adversary just has abstract handles to interact with the group. And now in those generic group models, we are actually able to prove hardness lower bounds. Because what we've just seen is that all the adversary can do is send queries to this oracle, and so we can count the number of queries that the adversary makes. And this way, we're able to prove lower bounds on group operations required to solve a problem. Shoup's GGM can also be extended to allow for pre-processing bounds. So this means we have some first adversary, which is unbounded, and it gets as input the entire description of the labeling function L. Then it can perform some unbounded computation and then send a bounded advice string to a second adversary. And then the second adversary is now bounded, and it obtains the instance of the problem, and it can start trying to solve the problem. This is a more realistic model because in practice, most crypto systems, they rely on a few standardized groups. So it's actually quite possible that an adversary can perform pre-processing on them. What we can also do in those models is we can transfer lower bounds between problems via reductions. And one way of doing this is to use the algebraic group model. So this is another idealized model where the adversary does see the description of the group, and it does get as input a real group elements. However, whenever the adversary outputs a group element, then it also needs to output some explanation of how it has derived this group element from the elements it has seen so far in the transcript. So in this case, this would be a vector of coefficients, alpha, beta, gamma, and then it needs to prove that the exponent of its group element is a linear combination of the exponents of the group elements it has seen so far. Okay, in this idealized model, we cannot prove lower bounds, but we can prove reductions between problems. And now if you want to transfer a lower bound in the GGM, you could try doing this. So you start with a problem A, for which you already know a GGM lower bound. And then to transfer this problem to problem B, you could try to find reduction against an algebraic adversary from problem A to problem B. Okay, this approach is nice because the reductions are so simple. You don't have any labels or any oracles that you need to take care of. However, if you want this approach to work, so if you want to this algebraic reduction to carry over this GGM lower bound, then you need to assume that any generic adversary is also algebraic. And this is only formally proven in Mauer's GGM. And in Shoup's GGM, it does not hold in general. Another downside of this approach is that it's not compatible with pre-processing bounds. And now what we do in our paper is we present a new technique to transfer GGM lower bounds, which is usable in Shoup's GGM, and it's compatible with pre-processing bounds. All right, let's take a look at the technical overview. So we consider reductions via geometric search problems. So we're in the same setting. We have two problems in the GGM, problem A and problem B. And then so far, I've always said, okay, we already have some lower bound for problem A. But how do you actually obtain this lower bound? Well, there are different ways. You could try to prove it in the GGM directly. But another popular approach is to first define a geometric variant of problem A, and then a reduction from the geometric problem to the problem A in the GGM. And then for this geometric problem, you can compute an information theoretic lower bound. Okay, so we have this lower bound for problem A, and now we want to transfer it to problem B. And the approach that we've just seen was this. You find a reduction from problem A to problem B using an algebraic adversary. Okay, in our paper, we went into a different direction. So we observed that you can also do this. You can also define a geometric version of problem B, and then find a standard reduction from geoproblem A to geoproblem B. So this means if you go this route, you also transfer the lower bound, but you don't need an algebraic adversary. And because you can get rid of this algebraic adversary, you can also move from the plain GGM to the bit fixing GGM. So that's the GGM that allows for proving preprocessing bounds. Okay, but in the rest of the technical overview, we're just going to consider the plain GGM for simplicity, and we're going to look at a specific example. So we want to now prove a lower bound for a CDH in the GGM using a lower bound for the geometric discrete log problem. And the first thing we're going to look at is this arrow right here. So we need to define a geometric version of CDH, and then we need to find a reduction. Okay, let's start with the definition of the problem. So we have a challenger and an adversary, and the challenger samples two elements from a field of prime order. And we will view those elements as coordinates of some point P in this coordinate system on the left. Now, what the adversary is allowed to do is it can query lines, and it asks if the point P lies on the line. In this case, it does not, so the challenger replies with 0. Now the adversary tries again, the point is still not on the line, so the challenger replies with 0 again. And now here in this query, the adversary has queried a line which contains the point P, and so the challenger answers with yes. Okay, so in prior works, when people looked at those geometric problems, they usually considered discrete log type problems. So there, the adversary really needs to find the point P. But here in this case, in a CDH type problem, the winning condition looks a bit different. So what the adversary needs to do, it needs to output a linear combination of x, y, and 1, such that when you take the target polynomial, which in the CDH case is x times y, and you subtract the output of the adversary, then this defines a polynomial. And you can see the 0 set of the polynomial on the left in the coordinate system in blue. And then we say that the adversary wins if and only if P is contained in the 0 set. And that's the game. And then in the paper, we show this reduction from the GeoCDH problem to the CDH problem in the GGM. And to give some intuition, so the reduction wants to use this generic adversary that plays the CDH game. And so it needs to simulate the GGM oracle. And it can do this using those line queries to the challenger to do this consistently. And then in the end, the generic adversary will output a label of the element G to the XY. And this label corresponds to this linear combination that we need to send to the challenger. Okay, this is very high level, and it looks a bit complicated right now, maybe, but you get used to it pretty quickly. And also, this is just a very specific example. So what we do in the paper is we look at a much more general problem. So we define a geometric versions of what we call a multi-instance Uber problem, which is a very general problem and more general than other Uber problems in the literature. And then we prove an analogous lemma to the one below. And we prove it in the GGM and also in the bit fixing GGM, which is the one that allows for preprocessing. Okay, and we try to define this problem as general as possible, such that when you make use this technique in future work, then probably or hopefully your problem will already be covered by your Uber problem. So you don't need to do this step again, and you can use our reduction in future work. Okay, so that's what's happening here in this arrow. And now we're going to talk about the other one. So we also need to find reductions between two geometric problems. And when we tried to do this, we've made this observation that many AGM reductions actually have a very natural analog for geometric problems, which is nice, right? Because the upside of the AGM reductions are that they are super simple. And it turns out that the reductions between the geometric problems are similar. So I don't want to go into the details, but what we do in the paper is we do the reductions for some examples. So we show a reduction between geometric versions of the Q-strong D-log to the Uber problem, which is similar to the AGM reduction that already exists in the literature. And then we also go through some other examples. Yeah, if you want to know what these problems are, just check out the paper. Okay, so that's what's happening here. And this concludes the overview of our technique. So to sum up, what we do in our work is we present a new technique to transfer lower bounds in the GGM. And we give new pre-processing lower bounds for several problems. What are the interesting open problems? Well, first, it would be nice to adapt the technique for decisional problems. In our paper, we just look at computational problems because we don't know how to define geometric versions of decisional problems, but it doesn't seem out of reach. So this would be something cool to look at. And the other one is to extend the bit fixing GGM to allow for decisional oracles and to work in bilinear groups. So yeah, because once you have this, then you can also use our technique as is, and it will also give you pre-processing lower bounds. So the only thing that's preventing you right now is because the bit fixing GGM needs to yeah, be extended to decisional oracles and bilinear groups. And that's it. Now I'm happy to take questions.
Yes, anyone has a question? Then maybe can you say a little bit about the difficulty of using this kind of geometric approach to study decisional problems?
Okay, let's see. Yeah, so I guess we tried for a while. Let's go back to the problem. Okay, so let's see, what would happen if we would want to define a decisional version of this? We somehow, yeah, the thing is in those geometric problems, you can see that the adversary does not even get an input, right? It's just, it knows that there's some point there and they can query the system. So let's see, right now I wouldn't even know how to, yeah, what the challenge for the adversary would be. But to be honest, it was a while ago that we thought about it, so I don't really remember the challenges.
Thank you. Any other question?
Following up to this question, there is a paper about an algebraic version of AGM. Maybe that the technique in that paper can be used to also define decisional version of a geometric problem. I don't know if you're familiar with that paper.
So wait, that's the paper.
I don't remember the title.
AGM, right?
Yes.
Yes, yeah, I'm familiar with the paper, yeah, but I mean, maybe it's possible. I don't think it's impossible, but we don't know how to do it. But yeah, thanks.
Okay.
All right, then let's thank Charlotte again.
Thank you.
All right, and the last talk in the session studies oracle separations for extremely lossy functions, and Felix Raubach is going to give the talk.
Thank you for the nice introduction, and this is joint work with Mark Fischlin. So yeah, I'm going to talk about extremely lossy functions, or short ELFs, which are families of functions defined by Mark's entry that either exist in injective mode or in an extremely lossy mode. So in injective mode, every image has at most one free image, while in the extremely lossy mode, the whole size of the image is at most polynomial. The mode is defined via a public key, which is either generated in injective or in lossy mode. And further, we want that these two modes are computationally indistinguishable. Now, also interesting because they can be used to replace random oracle model assumptions. So there have many attempts to replace random oracle model assumptions because it's not the same as the standard model, including correlation intractability, universal computational extractors. And extremely lossy functions is a new candidate here, which has the upside of only needing standard-ish assumptions and already being useful for quite many applications. So to construct an ALF, Zentry used the exponential decisional k-linear assumption, which is a generalized version of the exponential decisional Diffie-Hellman assumption. And he claims that these are probably true for example, elliptic curves. However, one question is whether we really need public key cryptography to build ALFs. So already Zentry was wondering whether maybe exponentially secure one-way functions or collision-resistant hash functions might be enough. And there has been a paper by Holmgren and Lombardi who introduced a primitive called one-way product functions. And also they were wondering whether they could build ALFs from this. So this motivates our main research question: what are the minimal assumptions for building these ALFs? We have two negative results here. So the first one is that there cannot exist a fully black box construction of ALFs from exponentially one-way functions, exponentially secure collision-resistant hash functions, one-way product functions, and many more. Indeed, anything that exists relative to a random oracle. We call that set oracle crypt in a nod to mini crypt, which is everything you can build from a one-way function. And actually, this turns out to be true even for just moderately lossy functions. So moderately lossy functions are functions that have in lossy mode an exponential size, but are at least compressing by 1 bit. On the other hand, we show that ALFs itself are also not enough to build a public key cryptography or key agreement, especially from it. So it seems to be that our standard symmetric primitives are not enough to build extremely lossy functions from, but it's also not necessarily something that belongs to the public key cryptography is queer. So I'll first talk a bit about our first result here. For that, we use an oracle separation, as Chris already mentioned. So we build a random oracle and a piece-based type oracle relative to which all these oracle primitives exist, but lossy functions and ALFs do not. And let me note that we use an idea from Piaczak, Rosen, and Seeger from TCC 2012 here. So the idea is as follows. So I'll first give you a very inefficient distinguisher. So if we look at the image size of the function relative to our random oracle, if it's in injective mode, clearly the function size has to be 2 to the n. While if we are in lossy mode, the image size of the function is at most half of that. So if we now introduce a distinguisher that just queries the function on each input, does all the queries to the random oracle, and thereby computes the image size of the function, and then decides whether the function is injective or lossy based on whether its image size is bigger than 3/4 of 2 to the n or less, then we clearly have a distinguisher. However, this distinguisher needs to do exponentially many queries to the random oracle, therefore surely cannot be efficient. However, it turns out that we actually don't need to query everything to the random oracle. Only the heavy queries are important for us. So query is heavy if it appears in f of x for at least a polynomial fraction of all x. I'll now explain why these heavy queries are important. And for that, first note that we want our hardness of the distinguishing between injective and lossy mode to be somehow dependent on our random oracle, because that's our source of hardness. So if we have some function that is injective for some random oracle O here. So for these two inputs, we have different outputs. Then we want that for a different random oracle O prime, the function isn't lossy. So for example, here we could have a collision between x1 and x2. Further, we need some observations about extremely lossy functions. And the first one is that lossiness is very much a global property, in the sense of if you go from an injective function to a lossy function, you need to change on average at least every second output, because now on average on every second output, you need to have a collision. And the other one is that the key generator that generates the public key either in injective or lossy mode itself has to be efficient and therefore only knows the random oracle at polynomially many positions. And therefore the other positions can't really influence the mode because the generator has to always give out an injective or a lossy function, or at least with overwhelming probability. So yeah. Let me go back to my previous picture. So if we now have to change at least half of the inputs X from injective to lossy, then at half of the inputs X, we need to have some or multiple queries to the random oracle that define whether we have a collision there or not. However, now our key generator only knows about polynomially many of these queues. So it has to reuse some of these queues over and over again, and thereby these queues become heavy queries. Now, it's very nice that heavy queries are actually quite easy to find. So what you do is you just query random inputs to F, see which queries F does to the random oracle, and collect all these queries in the set QH. And this QH, if you do it a polynomial number of time, of course, has polynomial size because F itself always does polynomially many queries to the random oracle. And because, yeah, you do that polynomially many times. But also with overwhelming probability, we know that all these queries, all the heavy queries are now contained in QH. Now with that, we can actually build an efficient distinguisher. We start again with our inefficient distinguisher. But now we only query all the queries in QH, which hopefully contains all heavy queries, to the original random oracle, and everything else we just sample new. So we basically have a new random oracle here, O prime, which only is the same on, with the original oracle on the elements of QH. Now, of course, if we now replace the original random oracle with our new oracle, the image size of the function might change. But we can argue that because basically the lossy function has to use these heavy queries, these non-heavy queries will only change the image size very slightly. And therefore, our distinguisher still decides correctly. That concludes our oracle separations, which now show that we cannot have a fully black box construction of else from anything in Oracle Crypt. And now also say a little bit about our second result. So there we want to show that we cannot build public key cryptography or key agreement from extremely lossy functions. For this, we use the well-known result by Impact, Diaz, and Rulich, that no key agreement can exist relative to a random permutation. Now what we do is we start by constructing an inefficient ELF oracle, which contains of a generator for the public key and an evaluation oracle, which both have access to a random permutation pi. And for these, we prove a simulation lemma, which says that there exists some efficient algorithm wrap with access to the random permutation, such that access to this algorithm wrap or to the ELF oracle is indistinguishable. And we note that this wrap algorithm doesn't need any global state. Now, we start by assuming that key agreement exists relative to our ELF oracle. So there exist Alice and Bob, and they speak with each other and the ELF oracle and agree on some key. Now, due to our simulation lemma, if we introduce our wrap algorithm here, this cannot change, it cannot break completeness of the key agreement, because otherwise we would have an efficient distinguisher against our simulation lemma. Now, however, because RAP is efficient, we can see this as two parties that just relative to random permutation agree on a key. So we know that there exists the Impagliazzi-Rudig adversary. And now in the last step, we again remove the RAP protocol, which we can do again, because otherwise we would have an efficient distinguisher. And so now we have an efficient adversary against our original protocol, and therefore a contradiction. So to conclude, we have shown that no fully black box construction of elves from anything in Oracle crypt can exist. But on the other hand, also that no fully black box construction of key agreement can exist from extremely lossy functions. So this leaves open what we actually need to use for extremely lossy functions. And I think this is quite interesting future work. And yeah, thank you. And I'm happy to take questions.
Questions? Then, we know how to build elves from exponential DDH, and now we know one-way functions are not enough. Do you think generic public key encryption is enough, or what's your, I don't know, or like, do we know elves from IO, or maybe IO is not enough? What is your, I don't know.
We don't really have any constructions, as far as I know, except for the Zentry constructions. So I'm actually not sure whether you can build it from public key encryption, generic public key encryption directly. So yeah, it's still there's nothing known. It would be really nice to have more constructions of extremely lossy functions. So yeah.
Or more lower bounds, but
yes, sure.
Yeah.
Do you need all the power of p-space for your separation, or what's the lowest complexity oracle you can use?
Well, actually, we need a bit more than p-space. So this is why there was some p-space plus, because we also need to sample a new random oracle, which is kind of hard in p-space. So we actually need a bit more than p-space. I'm not sure whether we can remove anything from p-space. Maybe.
Thank you.
Thank you for the question.
Okay, so according to my understanding, your results holds for moderately lossy function, right? Not so. Do you in any place use the extreme region?
I mean, yes, our first result totally holds. So we basically prove for lossy functions, because lossy functions are less strong than extremely lossy functions. But for our second result, it becomes a bit more complicated, because there, if you start with a stronger result, difference is a bit harder.
All right, then let's thank Felix again.
Hi, folks. So this is to remind you that nominally this session will stop at 4:45. And however, knowing what has happened before, and the bus driver said that the two buses will start waiting out there at 5, and they will depart no later than 5:20. So no matter how late this is, they will depart. Okay, so
welcome to IOPs and succinct session. The first talk is holographic snags for P and batch NP from polynomial hard along with errors, and Susumu will give the talk.
All right, so thank you for introduction. So I'm Susumu Kiyoshima from NTT. So this talk is about the succinct non-interactive argument or snag. So let me start from their definitions. So in snag, we have 3 algorithms, the generator, the prover, and the verifier. The generator samples a common reference string, or CRS, and makes it public. And given the CRS, the prover sends the proof to the verifier in a single message. The security requirement for snag are completeness and soundness, where as usual, the completeness requires that when the statement is true, an honest prover can convince the verifier, and the soundness requires that when the statement is false, any polynomial type cheating prover cannot convince the verifier with high probability. And in addition to these 2 security requirements, for snag, there is also an efficiency requirement called succinctness, which roughly says that the proof length and the verification time are very small. And in this work, we consider snag for a certain subset of the NP, and in particular snag for P and batch NP. In snag for P, the statement is an instance X over language in P, and it is considered true if a predetermined deterministic polynomial Turing machine M output 1 on input X. Regarding succinctness, the minimal requirement is that the verification time is much smaller than the running time T of the Turing machine M, which guarantees that the verifier does not need to run the Turing machine by himself. And usually it is required that the verification time is polylogarithmic in the running time T of the Turing machine M. In the case of snag for batch NP, a statement consists of a Boolean circuit and a bunch of input to circuit, x1 to xk, and it is considered true if the circuit and each of the input constitute a true instance of the circuit satisfiability, meaning that for each input xi, there exists a witness wi such that the circuit output 1 on input x1 and wi. So regarding succinctness, the minimal requirement for the case of snag for batch NP is that the proof length is sublinear in the number of inputs k, which means that the proof is not a simple concatenation of k witnesses. And usually it is required that the proof length is polylogarithmic in the number of inputs k. It is known that snag for both P and batch NP are very powerful and useful for many applications. And it is also known that they can be achieved under standard falsifier assumption, such as the learning with errors assumption, the decision linear assumption over bilinear groups, and the substantial hardness of the decision Diffie-Hellman assumption. Now, let us consider whether in snag we can make the verification time sublinear even in the length of the statement. So in particular, in the case of snag for P, the goal is to make the verification time sublinear in the length of the instance X. And for the case of snag for batch NP, the goal is to make the verification time sublinear in the total length of K input. So clearly, this is in general impossible to achieve because the verifier at least need to read the entire statement. But actually, it is known that this is possible to achieve if the verifier is given as a statement in a pre-processing format. For example, it is known that in some of the existing schemes, the verifier can be sublinear if it is given a short digest of the statement, which is created honestly before the verifier is given the proof. Now, the target of this work is a holographic snag, which achieve sublinear time verification by considering a verifier that is given Oracle access to a encoding of the statement. So instead of considering a short digest of the statement, in holographic snag, we consider long encoding of the statement, and the verifier reads only a small part of the encoding to achieve sublinear time verification. Recently, holographic snags have been used as a building block or as a cryptographic object, and in particular, they have been used to obtain two-round argument proximity, three-round zero-knowledge argument, and probabilistically checkable argument. Very roughly speaking, they are useful as a building block because in the existing scheme, the encoding of the statement has additional nice property, such as being information theoretic and locally testable. So at a high level, being information theoretic is useful to obtain round optimal protocol because if the encoding is information theoretic, we can encode the statement without sampling any cryptographic object as a setup, so we can save one round. And being locally testable is useful to obtain maliciously secure protocol because if the encoding is locally testable, the verifier can detect maliciously created encoding by making a small number of queries to the encoding. And in this work, we gave two holographic snags under the learning with their assumption. So one is for P and the other is for batch NP. And in both cases, we achieve good asymptotical verification time. And in particular, in the case of for P, the verification time is polylogarithmic, not only the computation time T, but also the length of the instance. And for the case of snag for batch NP, the verification time is polylogarithmic in the number of inputs, K. So prior to this work, holographic snag with such verification time is known as the designated verifier setting or under the sub-exponential hardness of the learning with errors assumption. So the contribution of this work is to obtain such snag under the publicly verified setting and under the polynomial hardness of the learning with error assumption. And as application of a holographic snag, we use an existing transformation to obtain a public coin 3-round zero-knowledge argument from a slightly superpolynomial hardness of the learning with error assumption and the keyless marriage collision resist function. So prior to this result, even though a private coin 3-round zero-knowledge argument are known from such assumption, public coin 3-round zero-knowledge argument are known even when only when the LW is sub-exponential hard. So there is a certain gap between existing 3-round public coin 3-round zero knowledge and the public coin private coin zero knowledge. And the contribution of this work is to close this gap by showing that slightly superpolynomial hardness is sufficient for LW, even for the case of public coin 3-round zero knowledge argument. So this is our result, and in the rest of this talk, I will explain how we obtain holographic snag from the learning with error assumptions. So our starting point is a recent non-holographic snag for P and batch NP that have been obtained from the learning with error assumption. And what is important to us is that these non-holographic constructions are non-holographic only because the verifier needs to compute the short digest of the statement. So this means that we can convert this non-holographic construction to a holographic one if we can somehow let the verifier obtain the digest of the statement in a holographic way. And since, of course, the prover does not necessarily compute the digest honestly, we need some kind of mechanism where the verifier can check whether the digest is created honestly or not. So okay, yeah. So the natural approach is to delegate computation from the verifier to the prover. And the main technical contribution of this work is is a holographic snag for appropriate set of hash computation, and in particular the hash computation that has been used to obtain the digest in the non-holographic construction. And we combine our holographic snag for hash computation and the existing non-holographic snag for P and batch P to obtain our holographic snag for P and batch N. And more concretely speaking, we construct holographic snag for two types of hash computation. So one is the macro hash computation, which we use to obtain a holographic snag for P. And the other is for summary extractable hash computation that we use to obtain a holographic snag for batch NP. So unfortunately, I don't have enough time to explain the detail of these two constructions. So we just give some key point of these two constructions. So regarding the holographic snag for summary extractable hash computation, one of the key points is that for our purpose, it suffices to achieve a weak soundness notion, which is defined carefully based on the definition of summary extractable hash function. So this is where we use the fact that we focus on the computation of summary extractable hash function. So very roughly speaking, it is weak in the sense that it does not guarantee the correctness of the global hash computation, but instead it only guarantees that the value we can extract from the digest using summary extractability must be consistent with the long input that has been supposed to be the pre-image of the digest. And another key point of our holographic snag for summary extractable hash computation is that to achieve holographic verification, we consider recursive construction where each recursion depends on a small part of the encoding. So in particular, each recursion can be verified by reading only a small part of the encoding. So we can achieve sublinear time verification in a holographic set. So regarding holographic snag for macro hash, we construct it by relying on the simple structure of the macro hash computation. So the detail can be found on the paper. So please check the paper if you are interested. So in conclusion, the main result of this work is a holographic snag for P and batch NP from LWE. And as application, we give public coins 3 round 0 knowledge from weaker assumptions than before. And by using this result, we close the gap between existing public coins 3 round 0 knowledge and the private coin. So this concludes my talk. So thank you very much.
Any question?
Thank you for a great talk. So I'm interested in what is exactly your soundness notion of the holographic snark for P? Because I know for like these digested RAM snark for P, it's only like you cannot prove two contradicting statements for the same hash. And now you have this like oracle access. So how can you like what your soundness is exactly is?
So even though the verifier has only oracle access to the statement is already fixed. So the soundness is standard, like the fixed. If the fixed statement is false, then the verifier cannot, as prover cannot give up access to proof.
Okay, thanks.
To get a similar result from the bilinear maps or DDH, which we know non-holographically, is there a fundamental problem, or what can you say about that?
I have not considered well, but now we use LW-based correlated interactable hash function to so that we can we can handle any like battle relation. So in the DDH-based construction, the class of battle relation we can handle is limited, and I'm not sure we can handle it. So I'm not sure this is the fundamental or not, but I have currently no idea about that.
Any other quick question?
Das ist
holographic snarks for Merkle hash also requires no signaling property, or
No signaling property. So the security proof we use is very similar to the non-signaling type approach, but I'm not sure it is essential or not.
Okay.
It's time to move to the next talk, so let's thank them again. The next talk is chainable functional commitments for unbounded depth circuits, and Russell will give the talk.
Thanks for the introduction. So my name is Russell, and today I want to talk about chainable functional commitments for unbounded depth circuits. And this is a joint work with David Barbas, Dario Catalano, and Dario Fiore. So first, let me give you some motivating applications of functional commitments. And so the motivating application is verifiable computation, or VC. So we have two parties, the client and the server. The client delegates the circuit gamma to the server, and then subsequently the client wants to evaluate this circuit gamma on some data sets, xi, and so they send this data set xi to the server, who computes gamma of xi, which yields yi, and sends the output back, together with a proof pi I certifying that the gamma of xi is indeed yi. So as usual, we want a VC scheme to satisfy completeness, soundness, and efficiency. The completeness says that if gamma of xi is indeed yi, then the proof should go through. And soundness is the converse, which says that if the proof goes through, then indeed gamma of xi is yi. And finally, for the VC scheme to be non-trivial, we want it to be efficient in an amortized sense. So namely, the time needed to verify the proof is faster than the time needed to compute gamma of xi, assuming that the client performs a one-time preprocessing on gamma. So next, let me tell you what a functional commitment is and how we can use it to build a VC scheme. So a functional commitment is a tuple of 5 algorithms: set up, preprocess, commit, open, and verify. And so to use this to build a VC scheme, the client does the following. So first, they preprocess the circuit gamma with respect to the public parameters, which use this BP gamma that they keep for themselves. And they send this circuit gamma to the server. And later, when the client wants to compute gamma of xi, they use the FC scheme to commit to xi, which yields a commitment from I and sum of serial input oxi. And they send this dataset xi and oxi to the server, who computes gamma of xi as usual. But now they also run the FC opening algorithm on the circuit gamma and oxi to yield an opening proof pi I. Okay, so in terms of security, we want an FC scheme to satisfy a weak security notion called evaluation binding, which says that it's infeasible to open gamma and the commitment to two different outputs, yi and yi prime. And note that this security notion is rather weak because it says nothing about whether yi and yi prime are indeed gamma of xi or not. It just says that they cannot be different. Okay, but nevertheless, it can be shown that this implies VC soundness, because if the server were to give us a valid proof for yi, which is different from gamma of xi, then the client who computed the commitment honestly themselves can honestly open this commitment to gamma of xi, which by assumption is different from yi, and then we break evaluation binding. And also to get an efficient VC scheme, we want our FC to be succinct, meaning that the time needed to run the verification algorithm is sublinear in the size of the circuit, description size of the circuit. So another motivating application is to bootstrap a snark. And in the previous talk, you already learned what a snark is, so I'm not going to repeat. So in order to construct a snark for all NP statements, it suffices to construct an FC scheme for, let's say, quadratic polynomials. And then we equipped this FC scheme with a special purpose snark, which is only used to prove the well-formedness of the commitment, but nothing about the relation. And this whole construction is, in fact, the snark for NP. So the rationale of doing this is that although we know that the snark requires non-falsifiable assumptions or non-black box reductions, still we want to minimize the component in our construction which requires non-falsifiable assumption. And here we use it for the minimal task of proving that the commitment is well-formed. And from a practical perspective, this gives us an alternative framework of constructing a snark, which could be efficient and competitive with existing approach. So, right. So what do we know about FC schemes? Well, before September 2022, then when we want to build an FC for some classes of functions, and if we are allowed to use snarks for NP, then we can trivially get FC for circuits. So that's rather boring. But as I said in the previous slide, this requires non-falsifiable assumptions, and it's not very satisfying. And so if we stick to falsifiable assumptions instead, then over the years, we managed to construct FCs for ever more expressive functionalities. So it's ranging from linear functions to semi-sparse polynomials, constant degree polynomials, or even NC1 circuits. Now, this is sufficient for bootstrapping a snark, but for the purpose of building a VC scheme, we want our FC to be as expressive as possible. So this year, there are 3 concurrent works which build functional commitments for circuits, for general circuits. So namely, there was the work of De Castro and Peikert and the work of Wei and Wu, who built functional commitments for bounded depth circuits. And in contrast, in this work, we built functional commitments for bounded width, but unbounded depth circuits. So let me summarize our results. First, we propose a new notion called chainable functional commitments, which is a generalization of functional commitments. So CFC in short. And we show how we can chain multiple CFCs for quadratic polynomials to get a CFC for unbounded depth circuits. And moreover, we give 2 constructions of CFC for quadratic polynomials, one from pairing assumptions and one from lattice-based assumptions. Both are falsifiable. And in particular, in the pairing setting, we built it from a new assumption called the hinted kernel assumption, which we proved to be true in the generic group model. And in the lattice setting, we built it from a twin version of the crisis assumption recently introduced in Crypto 22. And subsequently, it has been shown that this twin crisis assumption is actually equivalent to the crisis assumption. And finally, as a corollary, we obtain homomorphic signatures for unbounded depth circuits. Okay, so in the remaining of this talk, let me walk you through the first 3 points. So let me introduce what a chainable functional commitment is. And for that, let us recall functional commitment first. So as I said before, it consists of 5 algorithms: set up, preprocess, commit, open, and verify. And here I want you to pay attention to the open and verify algorithm. So because an FC is supposed to capture the functionality that you have a committed input X and you open this commitment with respect to gamma to an output Y. So this function gamma has a single input. So this is reflected in the opening algorithm, which takes as input only one single auxiliary input. And correspondingly, the verify algorithm takes one commitment as input. And also, we notice that the verify algorithm takes the output Y in plain text as input. And in terms of security, we have evaluation binding, which says that it's infeasible to open gamma and the commitment to 2 distinct Y and Y prime. And so generalizing FC, we get CFC. And basically, there are 2 changes. First, in FC, we have only a single committed input X. But in CFC, we have M committed inputs, X1 to Xm. And this is reflected in the open algorithm, which now takes M auxiliary inputs. And also the verify algorithm now takes M input commitments. And the second change is that the plain text output Y is now also committed. So we can see this in the verify algorithm, which now takes an output commitment instead of the output Y in plain. So we can observe that an output commitment can itself be used as an input commitment for further opening. So that's why a chainable functional commitment is chainable, as its name suggests. Okay, so let us see this chainability in action, or namely how we can build an FC for circuits from a CFC for quadratic polynomials. So suppose we are given a depth D circuit, gamma, and an input. So the first thing we do is to partition the circuit gamma into multiplicative layers, gamma 1 to gamma D, where each gamma I is quadratic. And we can compute the values of the intermediate layers as follows. So first we set the input layer x0 to be just the input x, and we compute x1 to be gamma 1 of x0, x2 to be gamma 2 of x0, x1, and so on and so forth, until we reach the output y, which is xd, which is gamma d of x0 to xd minus 1. So to produce a CFC opening of gamma and a commitment of x to the output y, the prover would do the following. So first they commit to the intermediate layers, namely x1 to xd. And then for each layer I, the prover would produce a CFC opening for gamma I and the input commitments of x0 up to xi minus 1 to the output commitment of xi. So we can easily see that the evaluation binding of the resulting FC for circuits follows straightforwardly from the evaluation binding of the CFC. Okay, so next let me say a little bit about our CFC constructions from pairings or lattices. So for the interest of time, this is just going to be a very high-level overview. So a commitment is basically an inner product between a commitment key and the message in Patterson style. And an opening proof is some sort of pre-image of some quadratic functions of the commitments. So now, since a commitment is just an inner product between a commitment key and a message, when we multiply two of them together, we get a lot of cross terms. And the difficulty that we solve in the construction is to manage these cross terms so as to avoid unwanted collision. And we solve this by introducing three types of commitment keys. We call them type alpha, beta, and gamma. And we can think of the type alpha as the main type. So to prove a quadratic relation, for example, Z equals F times X tensor Y, where the matrix F and the type alpha commitments of X, Y, and Z are available to the verifier, the prover would first give a type beta commitment of Y and a type gamma commitment of Z. Then they open F and type alpha commitment of X, type beta commitment of Y, to the type gamma commitment of Z. And then to complete the circle, the prover would prove that the two commitments of Y and the two commitments of Z are consistent. So for those of you who are interested, you can go through this slide, which is, I think, a bit easier to read than the paper. And so let me conclude this talk by taking this opportunity to advertise that we are hiring 2 PhD students in lattice-based crypto, and the job ad will appear in the ISL job board soon. Thanks.
Any question? If there are no questions, then let's thank Russell again.
Okay.
Okay. The next talk is multilinear short GP mod N and lattice-based succinct arguments, and Benedict will give the talk.
Thank you. This is joint work with Ben Fish. So we've already seen some definitions of zero-knowledge succinct non-interactive arguments, but I want to focus on two things. We have the security properties, the soundness properties. We sometimes have some zero knowledge properties, but we also have efficiency properties, and we can roughly separate them into the succinctness property, which says that the proofs, we can construct these arguments with succinct proofs, so the proofs themselves are short. And also the other one is a verifiable computation property, which says that the verifier itself is very efficient. I want to focus in this talk on two particular variants of these so-called, sometimes called folding protocols, or these are variants, very similar protocol to the bulletproof protocol. The bulletproof protocol is a succinct proof that works in discrete logarithm groups. And it suffices, or you can build a polynomial commitment from it, which is a specific type of functional commitment, and that itself then can be used to build snarks. However, there's two downsides of these arguments in these discrete logarithm groups. One of them is that they're not secure against quantum computer. They rely on the discrete logarithm assumption. And the other one is that they have linear verification time. However, there are alternatives. So it turns out that we can construct a very similar type of argument using lattice assumptions. So this is sometimes referred to as lattice bulletproofs. And it has one of the benefits is that it's plausibly secure against quantum computers. However, it also has some downsides. In particular, it has fairly low soundness. And the reason for that is that we only know how to instantiate it using a small polynomial-sized challenge set. And in order to deal with that, we have to repeat the protocol multiple times. That blows up the proof size. And also, naively, this protocol is an interactive protocol, but we might want to compile it to a non-interactive protocol using the Fiat-Shamir transform. And for protocols that have repetition, this becomes slightly more difficult. I don't want to go into details, but it basically becomes more difficult, and I might have to have even larger proofs. The other one is an argument that works in groups, so-called groups of unknown order. So this is, for example, the RSA group that is secure under the factoring assumption. And we had a work in 2020 called DARK that has one key benefit, which is that the verification time can be logarithmic in the statement. So unlike the bulletproofs argument in discrete logarithm group. However, it also had a major downside, which is that it was broken. And in particular, the scheme itself is not necessarily broken, as we'll see in this talk, but there was a significant gap in the security proof, which was found by Block et al. And they fixed the protocol. However, their fix also involved using small challenges, in particular using binary challenges, which again then blows up the size of the proof. So the results that we're going to show in this paper is that we can show security of both of these protocols using exponential challenge sets. So we can now, instead of having to use small challenges and repetition, we can actually show that these protocols are secure even if you use an exponential challenge set. And also we can do this using a unified treatment of both of these protocols. And this relies on two new results. One of them is a new Schwarz-Zippel lemma, modulo composites, so not just over fields, but modulo arbitrary composites. And then the other one is a new style of soundness notion that allows us to leverage this Schwarz-Zippel lemma, which we call almost special soundness. So let's look at the protocol, and let's look at a very simplified version of this bulletproof folding compression, which is that in each round, the prover sends two commitments, the verifier sends a challenge, and then somehow you take some random linear combination of the witness. And in the folding protocol, you do this for multiple rounds, but really it suffices to look at this simple sigma protocol. So when we want to analyze the security of this protocol, there's a very nice and natural, or there's a very nice soundness notion, which is called special soundness notion. Here is the multi-round variant of it, but basically it just says that I can extract from k different transcripts. And importantly, these transcripts are correlated in that they all have the same first message, but they have different challenges. And then if I want to extract this from, extend this to multiple rounds, then basically I can build this tree of transcripts where the challenges in the first round and the messages in the first round are the same, but then they diverge.
So how do we prove that this protocol is special sound? Well, this is actually two special sound. So we just need two transcripts, the red one and the green one. And it turns out then using a simple, the difference between the prover messages and the difference between the challenges, we can compute one of the witnesses, and then it's easy to compute the other witness. This is easy to verify. So the protocol has special soundness, but what if we try to transfer this to a lattice setting? So let's try to do kind of the same style of analysis. Again, we have two transcripts. However, one problem here is that suddenly we cannot invert anymore. Things are not, we're not in a prime order group anymore. So we cannot simply invert the challenges, which doesn't allow us to compute the witness directly. However, one thing that we can compute is we can compute basically this relaxed opening. What this is we can compute an opening to a multiple of the commitment. So R1 minus R2 is the difference of the challenges, and we can compute an opening to the differences of the commitments. And in fact, we can bound the size of this opening by 2 to the lambda. So it's lambda bits. However, if we try to extend this to multi-round protocols, well, let's look at this generalization. So let's look at a compressed sigma protocol for short openings, and we generalize this a little bit to arbitrary homomorphisms, and we basically want to show that there's a short preimage f of this homomorphism. And shortness we'll define this a little bit later. But the way that the protocol works is that in every round, the prover sends some commitments, and the verifier responds with some challenge. And then in the final round, the prover sends an opening to the commitment, and the verifier can check the commitment opening and also verify that this final opening is a small integer. However, if we extract from this using 2 to the mu special soundness, so basically a binary tree of depth mu, then we can compute an opening. We can compute, well, in fact, we can compute one of these relaxed openings. So we can compute an opening, so the original commitment is C, and we compute an opening of n times C. However, the problem is that the bit length of n, or that is going to be lambda times n. So the bit length, or basically the size of n that we extract is exponential in the original message length of the message vector that we've committed to. Yeah. So this is a problem because it basically then means that we have to use a commitment scheme. So we have to use a commitment scheme that is secure even for or that has a binding property even if T is very, very large. So basically, it turns out that the size of the commitment, so these commitments are still binding for these relaxed openings, and we can show that. However, the problem is that the larger parameters I want it to be binding for, the larger my commitment has to be. So concretely, this would imply that my commitments are linear. The bit length of my commitment is linear in n, and then suddenly my protocol is not going to be secure anymore, is not going to be succinct anymore, because every single commitment that I send is now linear in n, in the bit length. Okay, so how have these previous works dealt with that? Well, what they did is they used exceptional sets or special sets where all the differences of the challenges are invertible. So why does this help? Well, if the differences of the challenges are invertible, then basically I can extract something that is not necessarily a rational opening, and then I can bound the size of this slack parameter, this b parameter. And one very simple example is just this challenge set 1 and 0. There are slightly better sets than that you can use. You can use sets of polynomial size, but all of them are still going to be of polynomial size, and we actually have an impossibility result that implies that it's unlikely that with these sets we're going to do much better than that. And the problem is that this, because we only have a polynomial size challenge set, this means that the soundness of one iteration of the protocol is lower, which means we need to use repetition, which increases the proof size and also has issues if we try to apply Fiat-Chemie. So one interesting question is, and this is, the gap in the security proof in this dark paper was also very much related to exactly this issue of extracting rational openings. However, does this mean that these protocols are insecure? Well, this does not directly correspond to an attack. But what if we think about, let's take the adversarial perspective. Let's take the attack perspective. So if we consider an honest prover, then what the honest prover does, it commits to some vector f. And then at the end of this protocol, it sends this final opening. And it turns out that this final opening corresponds to some polynomial f, which is actually the multilinear evaluation of the original vector that I committed to, evaluated at the challenges. So f is a multilinear evaluation, or is a multilinear polynomial, and it is evaluated at f. And we know that in order to generate an accepting transcript, f evaluated at these challenges must be a small integer because the verifier checks this challenge. So what if the prover now tried to use a rational polynomial in the beginning? What if the prover in fact committed to a rational polynomial? So we can write this as some polynomial g of x, some integer polynomial g of x, divided by some numerator n. So if we see this, what this implies is that still the adversary, if it wants to succeed, needs to output an integer at the end. So what this means is that we know that g evaluated at the challenges divided by n has to be a small integer. So g of x has the coefficients g. However, if we think about it, if n is very, very large, it's actually it seems unlikely that this thing is a small integer. So how do we formalize this notion? Well, this is what we need to show is that g evaluated at these challenges divided by n is a small integer. And this is equivalent to saying that g evaluated at these challenges is equal to 0 mod n. However, we know n is not if n was a prime, our life would be easy because then we could apply the Schwarz-Zippel lemma, but we have no idea whether n is a prime. We have no prior information about what n is. However, so what we did is we developed a new Schwarz-Zippel lemma that works modulo composites and shows that if n is large enough for any n, this probability is in fact negligible. The other problem is that special soundness does not capture this perspective. So if we look at this statement carefully, this is a statement about the claimed witness G and the set of challenges. However, this doesn't really make sense because in special soundness, we use the challenges to extract the witness, right? So G certainly doesn't seem to be independent of the challenges. So what does it mean here that the challenges are run randomly? So in order to capture this notion, we had to define a new notion called almost special soundness, which implies knowledge soundness. I'll use the last 2 minutes to talk about this new Schwarz-Zippel lemma. So in the classical de Milo-Lipton Schwarz-Zippel lemma, this was invented multiple times, it says that a multivariate polynomial is equal to 0 mod some prime. This probability is negligible in lambda if I sample my variables from 0 to 2 to the lambda, and p is larger than 2 to the lambda. So this holds more generally for f over fields in integral domains. However, this does not hold for arbitrary commutative rings, and it's actually fairly easy to come up with counterexamples. So for example, if I show that f of x is equal to 0 mod p, then if f of x is equal to p times x, then for every second value of x, this polynomial is going to be 0. So this does not hold it generally. And even if we restrict to f to be coprime mod n, it turns out that for higher degree polynomials, this doesn't hold. But this does leave multivariate, so it doesn't hold for higher degree polynomials, it doesn't hold for, and we require that it's that the polynomial is coprime. But what we're able to show is that for multilinear polynomials, coprime with n, we can actually show that the probability is going to be negligible in the size of the modulus. So yeah, my time's up, and I encourage you to read the paper, and thank you very much.
So unfortunately, we don't have a time for question. So please ask question offline. So let's thank Benedict again. So the next talk is generalized spatial sound interactive proofs and their novelty soundness. And Thomas give you a talk.
Thank you. So this is joint work with my co-authors Serge and Nick. So we will be considering interactive proofs, which you all know for sure, but let me quickly introduce them. So these are interactive protocols between a proofer and a verifier, where the proofer claims to know a secret witness W for a given public statement X. And after some interactions, rounds of interactions, the verifier either accepts or rejects this claim. So interactive proofs have several desirable security properties, but we will be focusing on knowledge soundness. And informally, this states that dishonest proofers almost never succeed. So a dishonest proofer without knowledge of the secret witness W will not be able to convince a verifier with large probability. More formally, knowledge soundness is defined in terms of this knowledge extractor. And what does a knowledge extractor do? A knowledge extractor receives as input this public statement X and oracle access to a prover P star attacking the protocol, and its goal is to extract the witness W for the public statement X. And we say that an interactive proof is knowledge sound if it admits a knowledge extractor with large enough success probability and expected polynomial runtime. So it's typically non-trivial to prove knowledge soundness. You have to construct this extractor. So for this reason, more than 25 years ago, an alternative notion called special soundness was introduced. Benedict already mentioned this notion. And it is typically much easier to prove special soundness than knowledge soundness directly. So special soundness was originally defined in the context of Sigma protocols, which are 3-round interactive proofs. And suppose we have such a 3-round interactive proof in which the second message from the verifier to the prover C is sampled uniformly at random from a challenge set of size n. Then we say that such a Sigma protocol is 2 out of n special sound if you can extract a witness W efficiently from 2 colliding protocol transcripts. And 2 transcripts are colliding if they have the same first message A, but different challenges C and C prime. It is well known that 2 out of n special soundness implies knowledge soundness with knowledge error 1 over n, which matches the typical cheating probability, or the trivial cheating probability for typical Sigma protocols. So there are some natural generalizations you can require. For instance, instead of 2 accepting transcripts, you can require k of them. Then you also get knowledge soundness with knowledge error k minus 1 over n. And there's also there's also a multi-round generalization of this notion that was presented in the presentation before. And in this multi-round version, you need these 3 of transcripts to extract. I will be focusing for simplicity on the 3-round setting. So Benedict already mentioned a couple of drawbacks or limitations of this special soundness notion. And I will mention a couple of others and generalize this notion in another direction. So let us see where things go wrong. There are namely many interactive proofs for which you require additional structure to extract. So in some sense, the special soundness notion is a threshold notion. It states how many transcripts you need to extract, but sometimes you need a bit of additional structure. A very simple example is this standard amortization technique. So suppose we have this proof of knowledge where the prover claims to know n different pre-images for the homomorphism psi. And what this protocol basically does, it amortizes the complexity of the trivial n-fold the n-fold repetition of the standard Sigma protocol. So instead of proving knowledge of all the n pre-images one by one, it proves knowledge of a random linear combination of this random linear combination of the public values. So this is a very simple example, but what do you need to extract? You need a bit of additional structure. You namely need n different transcripts such that the challenges, C1 up to Cn, the bold-faced ones, which are now actually vectors, form a basis of your challenge space ZQ to the power n. Now, if we try to capture this by this threshold special soundness notion that we know, we see that we require q to the power n minus 1 plus 1 transcripts to extract. Because only if we have at least q to the power n minus 1 plus 1 accepting transcripts, then we know with certainty that they must contain a basis of this challenge space. Well, this property is useless because typically q is exponentially large, so this will render your knowledge extractor inefficient. So another example, I will not treat this one in detail, is a simple protocol for opening Merkle tree commitments. I just want to mention that this is an example that you encounter when you compile, for example, PCPs or IOPs into interactive proofs. And also here we typically end up with inefficient knowledge extractors. And there are several other examples, natural examples, where you run into this problem. What we did in this work is we define a more general notion of special soundness, capturing the above examples and some more. We construct a knowledge extractor for interactive proofs that satisfy this property. We also generalize to multi-round interactive proofs. We get a parallel repetition theorem almost for free. And then we apply this to a non-trivial example, which is the Fry protocol, which is an interactive oracle proof. So what do we do exactly? We define these monotone access structures, gamma, which are sets containing subsets of the challenge set. And all that we require is that this gamma is monotone, which basically means that if A is contained in gamma, then any set B containing A is also an element of gamma. And this is quite a natural notion in our context, because if we are able to extract from, say, A, then we are most certainly also able to extract from B. So then we say a 3-round interactive proof is gamma special sound if you can extract from colliding transcripts A, C1, Z1, up to A, CK, ZK, where the first message is the same, and the challenges C1 up to CK form an element of your access structure. So to give some examples, a K special soundness, then of course you get this threshold access structure where gamma contains all the subsets of large enough cardinality. For the amortization technique that I described, you need the span of S to, so the gamma contains all subsets that span the entire challenge space. And for this Merkle tree IP, it's also relatively easy to define the corresponding access structure. So then what we need to do next is construct a knowledge extractor for gamma special sound interactive proofs. And we do this by making the following observation. That's basically at any stage of the extractor, the challenge set can be partitioned into a set of useful and useless challenges. Typically, these extractors work by rewinding the proofer several times, and every time the proofer is rewinded, you try to extract an additional challenge or an additional transcript, and with a new challenge. And some of these challenges give you new information, and others won't give you any new information, and these are we call useless. So more precisely, we denote this by this function u gamma of A, where A denotes the challenges that you've already found, and u gamma A will then denote the subset of challenges that are remaining that will still be useful to you. So some examples for this threshold access structure: any challenge that you haven't found yet will remain useful. For this amortization technique, you will try to find challenges that are outside of the span of the challenges that you've already found, and similarly for Merkle tree IPs. So you have to be a bit careful in defining this notion of useful subsets or useful challenges. This is the formal definition, but let's not spend too much time on this. Let's just write down some of the natural properties. So for instance, challenges that you've already found will never be useful. further, this set of useful challenges is decreasing. So if you find more transcripts, then the challenges that remain, the set of challenges that remain useful grows smaller. And finally, if you've already found accepting transcripts for a set in your access structure, then there are no useful challenges remaining. These are quite natural challenges or properties. So then the main idea is actually quite simple. To find the ELT transcript, so somewhere in the extraction process, you simply rewind and sample a new challenge from the set of useful challenges. So we do this by adapting previous extractors. Again, you have to be a bit careful because for some extraction procedures, this approach fails, but fortunately for others, this approach works and everything comes together. What is important in the analysis is this crucial parameter, T of gamma, which nicely captures the refinement that we made. This T of gamma defines the length of the longest sequence of useful challenges that you can find. And the expected running time actually grows linearly in this parameter T of gamma, which basically means that knowledge soundness is implied. So gamma spatial sound interactive proofs are knowledge sound if T of gamma is polynomial. So this is a crucial parameter in the analysis and also when you apply these techniques. So to briefly summarize the implications of this result, we see here that we can always define this threshold spatial soundness parameter K of gamma. And now we have this refined parameter T of gamma. And we see, for instance, that if we look at the amortization technique, the parameter T of gamma is much, much smaller than K of gamma, where K of gamma was exponential, T of gamma is simply n. And the same holds for the other examples given here. Another example that was mentioned earlier this week was the notion of local spatial soundness. Also, local spatial soundness can be easily captured by this more general notion of gamma spatial soundness. So to briefly summarize, in this presentation, I introduced this more general notion of spatial soundness together with some of the tools to analyze it. And I claimed that it implies knowledge soundness. Well, in the paper, you can find the actual knowledge extracted together with the analysis. In the paper, we also have a generalization to multi-round interactive proofs. We have the parallel repetition theorem and the application to the Fry protocol, the interactive oracle proof. I must admit that there are some limitations when applying this extraction procedure to the Fry protocol. We have a discussion on that in the paper as well. Follow-up work will handle, for instance, the natural question, what happens if you take a Fiat-Shamir transformation of these protocols? This will appear soon on ePrint. And a remaining open question is how to improve our Fry extractor. There are some directions that we could explore. Thank you. I think there's still time for some questions.
Any questions? And let's thank Thomas again. The last talk to this session is a merge of two works. One is from polynomial IOP and commitments to non-malleable Zernari snarks, and the other is how to compile polynomial IOP into simulation extractable snarks, a modular approach. And Luigi and Mahak will give the talk.
Well, thank you. So, yeah, we're going to be talking about both of these works. And both of these works study non-malleability of zero-knowledge snarks that are obtained by compilation process from polynomial interactive oracle proofs. And the approach is going to be to identify easy-to-verify properties from polynomial commitments, which form the core part of the compilation scheme, and the PIOP. As an implication, we get a slight variance of Planck, Merlin, and Lunar when compiled with the KZG commitment scheme are non-malleable. So why do we want to study simulation non-malleability? Because the standard definition under which we safeguard against a correct prover is via knowledge soundness, which, like the previous talks mentioned, it says that a correct prover cannot come up with a proof without knowing the witness. But notice that in this definition, there's a single tuple of statement and proof, and in particular, it doesn't talk about more proofs. But realistically, a correct prover probably gets to see multiple proofs and can launch a malleability attack where it just takes a previously generated proof, mauls it, and outputs that without knowing the witness. So now you cannot extract from that. For that, we need to go to a stronger definition called simulation extractability, which implies non-malleability. And here, the prover gets this additional power of seeing multiple proofs via simulation queries. And then later, we ask the extractor, we require that the extractor should still be able to extract a valid witness from an accepting proof. So this problem has been studied in the past for existing succinct snarks. And the gap in all of these approaches is that even though they try to provide a generic enough framework, the analysis at the end of the day is still very specific to the protocol. So a question that we try to answer in both of these works is, well, is it possible to claim non-malleability for a large class of existing snarks without having to go into the details of each of these proof systems? And to do that, because we want to answer it for a larger class of zero-knowledge proofs, we look at a common paradigm of making these proofs, which is via compilation of PIOPs. So, right, so you design an information theoretic proof system called a PIOP, and then you compile it using a knowledge sound commitment scheme, polynomial commitment scheme, and then to get non-interactivity, you put Fiat Tremere on top, and that gives you the final knowledge sound ZK snark. And we want to look at this because there's a long line of snarks that are built using PIOP. And in particular, we want to look at the KZG commitment scheme because that's the scheme that's used by a lot of these papers for the final compilation. So just a little bit about how this compilation works. In the PIOP setting, the prover wants to prove a statement, and to do that, he comes up with these polynomials and puts them as oracles in the sky. And in return, the verifier sends some challenges back, and this can happen for a bunch of rounds, towards the end of which they reach the query phase, where the verifier can query these oracles for evaluations. And that's modeled as a query algorithm that takes input as all the challenges, and then outputs which polynomials should be evaluated at what point. And the verifier can evaluate them directly from the oracles. To compile it, the prover, prover will commit to these polynomials using a polynomial commitment scheme, which allows you to commit to polynomials and then later open evaluations to them along with proofs of correct evaluations. And then obtain challenges from the random oracle, and then towards the end, it would output the evaluations and also these proofs of correct evaluation. So the transcript consists of all the commitments, challenges, evaluations, and the proofs. And for this approach, we take different approaches to get to the same result. The first one that I will be talking about follows a proof template from previous papers that attempt to do the same thing. And this template works for other proof systems other than just PIOP-based ones. And here you want the proof goes as follows. If the underlying ZK snark is knowledge sound, has trapdoorless zero knowledge, and satisfies some variant of unique response, then that would imply simulation extractability. But the difference here is that all of the prior works look at the final result of ZK snark, and here we will try to look at the smaller pieces, PIOP and the commitment scheme, and identify properties from these objects. And the variant of unique response that we would use is called weak unique response, which I'll explain what that is later. And the second approach is a more direct one. So notice that the knowledge soundness of ZK snark is tied to the knowledge soundness of commitment scheme. So if you could come up with a notion of simulation extractable commitment scheme, then that would maybe give you simulation extractable zk-snark. So the second approach is to come up with this new notion for the commitment scheme. All right, so I'll talk about the first one, and then Luigi takes over to talk about the second one. So here, the goal is, so this is the template that we want to show. And I will not talk about knowledge soundness because that's typically proven. I will talk about how to generically show chapterless zero knowledge and weak unique response, and then basically fill this table for PIOP and commitment schemes. So chapterless zero knowledge just means that, the zero knowledge simulator doesn't need any trapdoors for simulation. It can observe and program random numerical queries. And one of the theorems that we have in the paper is a very basic one, says that if your PIOP has honest verifier zero knowledge and the commitment scheme is hiding, then that gives you chapterless zero knowledge for the compiled zk-snark in a generic way. And both of these properties are standard, and you show them anyway while giving the PIOP and commitment scheme. And we have a second theorem in the paper, which works for weakly hiding commitment schemes, which allow you to leak some information about the committed polynomial. So for instance, deterministic commitment schemes. And to get chapterless zero knowledge for that, we define a stronger notion of honest verifier zero knowledge. So basically, we say that if there is some randomness to begin with in the PIOP, then you don't need randomness in the commitment scheme. And for the final property, weak unique response, that means that an adversary cannot reuse a simulated transcript. So it cannot come up with a transcript which shares a common prefix with a simulated transcript. And then the ith prover message is different. To show this, well, the properties that we identify here, the first one is we need that the PIOP has high min entropy for the query algorithm. So recall that towards the end of the PIOP, there's a query algorithm that takes in input as the challenges and outputs what should be evaluated. And we say, we define this as, if you change the inputs, if you change one of the challenges, then it changes what should be evaluated. And we need a second property, which is just that the first polynomial shouldn't be evaluated at all distinct points, like all degree plus 1 distinct points, which just means that don't reveal the entire polynomial in the open to the verifier. From the commitment scheme, we need the standard hiding and binding, and unique evaluations proofs, which is not the most standard property, but for KZG scheme, we show it in a very simple way that, yeah, it satisfies it. And similarly, we have a second theorem which works for weakly hiding commitment schemes and then requires some additional properties from the polynomial IOP. And yeah, so that's the end of my part.
Thank you, Mark. So even though we wanted to achieve a similar goal, we took a different perspective, as Mark was saying. So let's recap again the usual transformation from PIOP to SNARK using polynomial commitment and Shamir. What we can observe is that the derived ZK SNARK is not always simulation extractable. For example, let's assume that we use a polynomial commitment which is fully malleable. In theory, one could transform a simulated proof, which is just a proof over a bunch of commitments, into another proof. So yeah, we cannot extract it. We cannot extract a witness from this. So we took this other approach. So let's try to see if we require some stronger property at polynomial commitment level. Do we achieve then simulation extractable ZK SNARKs? Well, in theory, it could be possible, but this would not capture existing constructions because we know that polynomial commitments like KZG, they cannot be simulation extractable because they are malleable. So KZG is this very famous polynomial commitment. It works on bilinear groups. The structured reference string is a tower of powers for a secret point test. In order to commit, you just compute the polynomial in the second point. The evaluation proof is the quotient polynomial committed. And in order to verify, you just need to check that the quotient polynomial multiplied by the secret point minus the evaluation point is equal to the commitment shifted by the evaluation value. And you can check this just using two pairings. KZG is linearly homomorphic, so it's also malleable. Just consider two simple malleability attacks. Given a proof pi for a commitment C opening to a point X to a value Y, the proof pi is also a valid proof for other commitments. For example, the commitment C shifted by any constant delta when open to in the same point X, but to the value Y plus delta. And we can also use pi on arbitrary point X star. So we may derive a commitment as C minus the quotient polynomial multiplied by X star minus X. And this is a valid proof on the point X star. The fact is that even though these are malleability attacks to KZG, these are not sufficient to break the simulation extractability at snark level. This is true if the PIOP is what we define compiler safe, so that all the PIOP polynomials are evaluated on the last round coin of the verifier. So we cannot require then a polynomial commitment to be fully simulation extractable, but maybe we can require some policy-based simulation extractability, which is just a generalization of the usual simulation extractability experiment. And we identified a policy that is both sufficient for this compiler to work, but also met by KZG. What is this policy-based simulation extractability? Well, just take the usual experiment in which the extractor needs to extract, but then let's prepend a very simple if clause. So if the policy is satisfied, then the extractor must extract. We already have a lot of such policy-based simulation extractability in the literature. For example, this weak simulation extractability. There is a constraint at extraction time. So the extractor needs to extract only if the statement is fresh. Or we can have constraints at simulation time. So the adversary is only allowed to ask simulations for true statements. And the policy under which we prove KZG to be simulation extractable holds in the algebraic group model and the random oracle model. It has some simulation constraints and extraction constraints. As for the simulation constraints, we require the adversary to choose a set of points, and then he can only ask simulations on these points. So this can be arbitrary, but non-adaptively chosen. And we also require some form of what we call algebraic consistency. So for example, on the same commitment, in the same point, the adversary cannot ask for two proofs to two different values, evaluation values y. Instead, for the extraction constraint, we require that the point x star on which the extractor forges needs to be sufficiently random and also chosen after the commitment C star. Well, we also need to make some extra adjustments to this to the original recipe, because the PIOP does not only have to be compiler safe, but we require the verifier to be non-adaptive and algebraic. So in particular, this means that the queries of the verifier are independent of the statement. And also we require the existence of a commitment simulator. So there exists a way to a strategy, a way to simulate that is linear with respect to a vector of simulated commitments. This is basically given for free when the commitments are hiding, or may require some computational assumption if not. And these two constraints are actually very easy to meet in practice. For all the PIOPs that we looked at, these were met. Now, to wrap up, the reason why on this stage you have seen two people and not just one presenting a joint work, our two approaches achieve similar goals, but there are also a lot of differences. So in particular, as Mark was saying, they require, they assume that a trapdoor-less simulator, while we rely on a trapdoor simulator. They derive the weak unique response property from the unique proofs of polynomial commitments. So for example, they analyze the case of KZG, while we require the stronger property from the polynomial commitment. And this also means that while their approach was in a way easier for KZG and does not require the AGM, our approach was somewhat more involved, and also it strongly leverages the flexibility of the algebraic group model. As for concrete schemes, while they capture Planck only with hiding commitments, we are able to capture Planck even with deterministic commitments. We also share some common limitations. So in particular, we are not able to capture Marlin and Lunar as they are described in the original papers, but just slight variants of these protocols. We both require programmability of the random oracle, and we are not able to capture the fully optimized PIOPs. So in particular, the ones that are actually deployed in the real world. For example, there is this Moller trick or linearization trick that we are not able to capture. Even though these seem like open problems, there is some ongoing work on basically all of these 3 bullet points. So hopefully they will be fixed soon. Thank you, everyone. We are here for questions.
Oh. Yeah, very nice works. I guess I had 2 questions. One was regarding the last thing you said. Do you think there's any chance that these protocols are actually malleable or not? And
which protocols?
like you said that the like Marlin or Lunar is described in the paper, you're not able to prove that they're simulation extractable or things that use this linearization trick. Is it possible that they're actually malleable, or do you think it's just our techniques are not good enough yet?
No. We do not capture them at the current level with the current work, just because we made some simplifying assumptions. But the ongoing work that we have on Marlin and Lunar seems to confirm that they are not malleable. They are simulation extractable under some constraints. In particular, you cannot use every polynomial commitment to prove that Marlin and Lunar are simulation extractable. So, for example, on the just to make an example with Marlin, you cannot use non-hiding commitments. Sorry, hiding commitments in the last round of Marlin.
Okay. And then the other question is, so both of these approaches work for polynomial IOPs, but is it, do you think similar techniques would work for, like functional IOPs with then a functional commitment? Like this sort of this same pipeline, should that work as well?
Well, I can only talk about the approach that I took.
Yeah.
I think it would, but I think everything should be, again, modeled and syntactically changed to capture different notions and polynomials. Yeah.
Okay. Very cool thing.
Just maybe one minor. Yeah, I think we also looked at some other IOP models, like the one in which use multilinear, for example, polynomials. We do not have results on this, but yeah, there is some intuition that we may use or reuse some of this work.
Any other question? This is the end of the session and all the talks today. So let's thank all the speakers again.
Conference announcement. Okay, so I'm Miriam Huang, and I'm in the conference like participant and also like your night market tool guide. Yeah. So other people who wear like a yellow T-shirt are also, or Kaimin students are also your tool guide. Night market tool guide. So yeah. So after like arriving at the night market, you can either choose to follow us. Follow like the yellow T-shirt tour guides, or just like explore the night market on your own. Yeah. So we have 2 shuttle buses.